Hello and welcome to this new course in which you will learn how to troubleshoot your electronics projects easily and effectively following simple steps. This is Ashraf from Educational Engineering Team. So, are you stuck with a project that isn't working or isn't functioning properly? In this course, we are going to introduce troubleshooting techniques to help you efficiently fix your project without having to call someone else or to throw your projects on the garbage. Sometimes when you work on a project, things just don't go as planned. When that happens, you have to determine what went wrong and when it went wrong. If you are lucky, the problem is easy to spot and fix. Other times, you can find yourself poring over code, disconnecting and reconnecting components, and struggling to remember why you wanted to do this project in the first place. You will feel disappointed, and in this course, we will help you fix any project and get it up and running in no time. It's a rite of passage for every maker, and over time, each of us develops a few debugging and troubleshooting strategies. In this course, I want to share a few fast and easy troubleshooting methods specifically for beginners and intermediate users, and we will also provide a troubleshooting checklist to keep handy as you work through your projects. I'm sure that you will enjoy this course content, and things that will be covered in this course includes troubleshoot circuits on a breadboard, debug your code, and the best techniques to do so. You will also learn how to check the items or electronic component specifications, and we will talk about some useful tools for troubleshooting. Then we will take a hardware troubleshooting checklist and a software troubleshooting checklist. After that, we will have a separate section where we explain the basics of electronic components troubleshooting, and we will also provide you with a free troubleshooting for electronic components book where you can get once you join this course. We sell it on Amazon, but you will get it for free. We will also provide electronic and electrical devices maintenance and troubleshooting section, and you will get to download a free troubleshooting checklist. This course is full of information, and I'm very sure that you will gain a lot of knowledge, and it will help you in your, let's say, project making career, or even if you are a geek, you will get a lot of useful information from this course. Can't wait to see you inside. This is Ashraf from Educational Engineering Team. Educational Engineering Team. We are a team of skilled engineers sharing knowledge with the world. Educational Engineering Team is a leading team in microcontroller industry with over 12 years of experience in teaching and doing practical projects. We strive to put all our hands-on experience in these courses. Instead of superficial knowledge, we go into the depth of the topic to give you the exact step-by-step blueprint on how to tame simple as well as complex topics in easy and bite-sized videos. This real-world knowledge enables you to grasp knowledge easily, and you can apply this learning immediately to your life and projects. Educational Engineering Team has been in the programming and microcontroller business since 2007. We have been part of many projects over the course of these years, and we have gained a good insight into students' and educators' needs. We are passionate about sharing all our collective knowledge with you. As of 2020, we have already taught over 250,000 students and counting. Currently, we have more than 100 courses on Udemy. Ashraf, who is the educator and author of Educational Engineering Team. Ashraf is an educator, mechatronics engineer, electronics and programming hobbyist, and maker. He creates online video courses on the Educational Engineering YouTube channel that has more than 4 million views and 20,000 subscribers. And he is also an author of 4 microcontroller books. As a chief educational engineer since 2007 at Educational Engineering Team, the company he founded, Ashraf's mission is to explore new trends and technology and help educate the world and make it a better place. Educational Engineering offers educational courses and boot camps, articles, lessons, and online support for electronics hobbyists, programming hobbyists, microcontroller hobbyists, STEM students, and STEM teachers. That team also work as a freelance engineers, helping many students in their graduation projects and provide guidance and consulting for many students over the years to help them kickstart their career. Ashraf's core skill is explaining difficult concepts through a step-by-step, easy-to-understand matter using video and text material. With over 11 years of experience in teaching, Ashraf has developed a simple yet comprehensive and informative style in teaching that students from all around the world appreciate. His passion for microcontrollers and programming, and in particular for the world of Arduino, PIC microcontroller, Raspberry Pi, has gained his personal development and his work through educational engineering. Ashraf's online courses helped over 250,000 people from around the world to be better and to make a great career in the industry. Educational Engineering Team offer courses on circuit design, simulation, and PCB fabrication, Arduino, PIC microcontroller, and Raspberry Pi, programming in C, Python, and other programming languages, in addition to PLC industrial programming and automation. We also offer courses in 3D design and simulation, and we cover ESP and Internet of Things world. Now, for more information, you can use the links in the profile page to follow Educational Engineering Team and Ashraf's latest innovation. We can help you make any idea into a real-life project. So if you have any graduation project idea or any concern, any question in microcontroller and embedded system, we are here to help. You can simply reach out to us using our profile. You can look up for Educational Engineering Team using Google and send us your question. We are here to help you. Thanks for watching. This is Educational Engineering Team. Troubleshoot circuit on a breadboard. Over time, breadboards tend to wear out and oxidize, which means that components may not make good connect or good contact. So the first thing that you can do is check the connections of the components in your project. If you suspect that your breadboard might have oxidized, it can help to remove a component and stick it back in a couple of times. If your breadboard contacts loosened over time, it can help to gently push down on the components while you test your circuit. I found this to be especially helpful in designs that use a lot of jumpers or jumper wires, because those connections can easily come loose. Another tip is to use color coded wires. For example, you can use black wires for all the ground connections, green wires for data transfer, and so on. Incorporating color codes helps to keep track of what is already connected, and it also makes it easier to notice if something looks out of place. What I usually do is use color coding, which is the first step: black for ground, red for positive power supply, and yellow for signals. This will help you easily recognize any missing wire, and if you don't have power in your circuit, you will know that you have to check the black and red wires because they are responsible for wire or for power transferring. And you need also to make sure that your breadboard is usable. Sometimes when you use a breadboard so many times, it become unusable. You won't have any connection between the pins because you used it so many times that these pins are now, let's say, they are dead. So you have to replace it with another breadboard. Make sure that you are choosing a good breadboard type because there is a lot on the market and not all of them are very good. So don't go for the cheap ones. And if you have problem purchasing one, you can send me a message or ask us in the Q&A board. We can recommend a breadboard for you. Thanks for watching this lesson. This is the first step in your troubleshooting. If you are just making a circuit on a breadboard, make sure that your breadboard is usable, use color coding wires, and make sure that your pins are not loosey so they did connect. Thanks for watching this lesson. If you have any question, please ask in the Q&A board. Debug your code. So you checked all of your breadboard connections and still can't get the project to work. The next step is debugging or checking your code. You can often use a debugger to make sure that your program behaves as expected, but unfortunately it's not always that simple. The Arduino IDE, for example, doesn't come with a debugger. Luckily, you can still check whether your code behaves as expected or not by adding a debug output to your code. In the next lesson, I will show you a practical example of a code where we place a debug code inside our Arduino code. For now, what you need to know is that many modern IDEs include a built-in debugger to help out as you write your code. There are also options like Visual Micro for Visual Studio that offer users the ability to write, edit, and debug specifically with Arduino. A lot of other softwares like Micro-C and other code writing softwares provide their own debuggers. So make sure that you check the software company website and read their tutorials about how to use the code debugger. It's very important to debug your code to make sure that your code is free of logic and syntax errors. As I mentioned earlier, we are going to explain a simple Arduino code in the next lesson where we place some debugging code inside our original code to make sure that it's functioning correctly. Thanks for watching this lesson. If you have any question, please ask in the Q&A board. Check the specifications. Now, electronic components are usually meant to be used in a specific way. If you attempt to use them incorrectly, your design could first not work, or behave unexpectedly, or get damaged and become unusable. Checking the datasheet for the parts in your design is an important step when troubleshooting. Now, people let's say they misunderstand what troubleshooting a datasheet or a component using a datasheet is. So here we are going to see a simple example for a component that has different numbering for the pins depending on one changed letter. Now let's check the datasheet for that component. Now let's go to our browser, write google.com, and here write, let's say there is an IC that I use, TLC pinout. Now if you head over to the images, as you can see here we have a TLC 59 and here we have another TLC 59. Now by looking to these two, you can see that number 1, which is the first pin here, is for out 1, while number 1 here is for ground. So these two pin outs are for different versions of the same IC. You have to make sure that you are using the right pin out. Sometimes when you write your IC like this, you will find more than one version, so you have to write the whole number. It's called TLC 5940, and if you have any other letter after this number, you must write them down here so that you can get the right connection. Now we can see from this that this is the right pin out for our IC, and this is the one that we are going to use in our circuit. Now if we use this one, everything will be different. As you can see, I have to connect ground to this pin, while ground here is connected to pin 22. So this will most likely burn out the entire project or the entire circuit, and without giving or without taking into consideration that this IC will burn out as well because we provided power to the wrong pins. So always make sure that you double check the datasheet of your component because they contain valuable information, including timing descriptions, pin diagrams, maximum ratings, and much more. So write the whole number, write pin out, or you can simply write .pdf, and you will get the first result as a PDF for your IC, and you can then check it out and make sure that you have the right IC. These are the main features in the PDF, and from here you can see the table of contents, and you can go to the power dissipation calculations, or you can simply drag and come here. As you can see, now it's telling you that there is two packages. The first one is anti package with 28 pin, and this is the pin out. Now if you have the PWP package, this is the pin out for it. So make sure that you use the right pin out for your package, and you are choosing the datasheet for your IC correctly, because this type of information is very valuable. If you have any question or if you have an IC that you don't know how to connect, you can ask us in the Q&A board. I'm here to help you. Thanks for watching this lesson. This is Ashraf from Educational Engineering Team. Useful tools for troubleshooting. As a maker, you should invest in a good multimeter because it's a versatile device that will help you with your projects. If you use a breadboard, you can utilize the continuity function of the meter to make sure that two pins are connected as intended. This can also be used to search for short circuits. Furthermore, the voltmeter functionality can help you check the state of signals that change slowly. The ammeter can be used to monitor the current flowing through a component to make sure that you don't exceed its maximum rating. Consider investing in troubleshooting tools like a voltmeter. As your project gets more sophisticated, you should think about getting an oscilloscope, especially if you have a project with rapidly changing signals. The oscilloscope represents the voltage of a signal over time so that you can track whether it's what you expect or not. If you don't have either of these tools, you can also utilize a LED with a built-in resistor to check whether a signal is high or low. However, that is a very crude method, and it's only suitable for very simple tests. So, in this image, you can see that we have some tools that I recommend having: a digital multimeter, a cutter, a wire cutter, iron head for soldering, a meter, and some screwdrivers, plus a note so that you can check your checklist that we will discuss in a separated lesson. Again, voltmeter is enough, but if you have a rapidly changing signal, you have to buy an oscilloscope, since it gives you further details about how your signal behave over time, and it's a very useful testing tool. Other than that, you can check our checklist for the tools that you should have in your library so that you can investigate your projects and to get your project up and running in no time using the right tools. Thanks for watching this lesson. If you have any question, please ask in the Q&A board. Troubleshooting checklist, the hardware part. Now, here we have a list of questions that you can use to troubleshoot your project. Now, the first thing is it powered on? Do you have the right power connection? Do you have the right voltage and current supply to your circuit? Is the power connections are connected correctly and in the right order, positive and negative? If all of these checks out, you can move to the next one, which is the voltage correct? Sometimes we have an IC that works with 3 volts and we are connecting 5 volts. We have to step down the voltage so that this IC can work properly. Make sure that each item has its proper voltage level. Then ask yourself, is the current limit of your power supply exceeded? Sometimes we have a lot of components connected that are power hungry, and we are using a simple charger that provides 500 milliamp. Our project usually will require 1 or 2 amps, and we are only using 500 milliamp. Make sure that you have the right power supply with a current limit that is higher than all of your components' power consumption, or current consumption in that case. Move on and ask yourself, are all the components correctly connected? Make sure that you double check the datasheet if you have an IC or a component that has a lot of pins and you are not sure about whether these are the right connections for these pins or not. We already explained this in the check the specifications lesson. Make sure to check it again to make sure that the datasheet that you have is for the component that you are using. Ask yourself, are any components broken or faulty? Sometimes, in a lot of circuits that I do connect, there is a crystal oscillator or a capacitor that is not functioning. Sometimes you buy it like that, it's not functioning, and sometimes you are the one who's breaking it by connecting this component the wrong way or forcing it in so that it won't function anymore, or some of the internal connection are lost. So make sure that if you suspect a component, change it with another one, and keep doing that for other components that you are not sure if they are functioning correctly or not. Then, after doing all of this, make sure that no loose connections are there. Double check each wire, each pin, and make sure that they are all connected together. Sometimes it will help to use a multimeter continuous test to make sure that there is no short circuit and all components are connected correctly. Does it help if you gently push down on your circuit? Sometimes some components are connected, but they don't really provide connection if you are not pressing them down. So try pressing some ICs, some components down, and see if your circuit will function. Are your ICs connected correctly, and did you check the datasheet? Now, this is like, are your components correctly connected? But you have to double check the datasheet again. Sometimes you are missing something and you are too, let's say, ignorant to recognize it. So you have to double check that again and make sure that your item has only one datasheet. Do you fully understand what the ICs are supposed to do? Sometimes understanding what an IC in a circuit is doing will help you investigate that IC and making sure that it's functioning the way it's supposed to. Is your design correct? Now, sometimes what works in simulation doesn't work in real life. So make sure that your design is correct and that your components ratings is correct and you are connecting them the right way. Sometimes it helps a lot to reconsider your design or getting another design that someone else did try and try to connect it instead of your design. Again, what works in simulation doesn't necessarily have to work in real life. Now, if you have done all of these steps, I'm very sure that you will get rid of the hardware part of the problem. Now, another step that I usually do is use the digital multimeter to check the inputs and outputs to each component. So if you know that the power source must supply 5 volts, make sure that you turn on your voltmeter and check the voltage measurement for these 5 volts. And the same thing for other ICs and their outputs. If you have any question, please ask in the Q&A board. I'm here to help you. Thanks for watching. This is Ashraf from Educational Engineering Team. Troubleshooting checklist, the software part. Now, in order to troubleshoot our software, first we need to ask, are there any endless loops where they don't belong? Sometimes we place an endless loop, and when our codes enter the execution phase, it does enter one of these loops and it never gets out of it. So make sure that you don't use a lot of loops unless they are necessary, and don't use endless loops, because an endless loop means that your code will keep repeating what's inside this loop forever and it won't get out of it. Now, the second step is asking yourself, does your code contain unreachable code? Make sure that the code that you are writing is, let's say, following a certain flow. Sometimes when you write a code, you use methods, and these methods are never called. These line of codes are never reached. Make sure that they are reachable and usable by the rest of the code before moving forward. Next step is, did you forget to initialize a variable? Sometimes when compiling your code, you will get an error if a variable is not recognized, but some software assume that this variable is already defined, or they don't provide the proper coding and compiling messages for errors and warnings. So make sure that all of your variables are defined correctly and there is no, let's say, overlapping. You are not using the same variable name in more than one location without a purpose. Then ask yourself, did you forget to call a method? Methods are tricky. Sometimes we define a method, we write a bunch of code inside it, and we forget to call it inside our code. This will cause our code to function unexpectedly, and we need to make sure that the methods that we are writing down are used in our main code. Now, which parts of your program are executed? You need to try debug outputs, and we are having a separate lesson for debugging your code, but you need to make sure that your program is executable, and when you compile it, you don't have errors or warnings that might end up with getting an unfunctional or non-functional project. Now, the last question is your program correct? Sometimes you write a program and you assume that it's correct, but it doesn't work. This is one of the dumbest mistakes that I did make and a lot of you will make. We try to do our best writing a program or a code and we assume that this code will work. Now, once we hit compile, we don't see any errors and we say, yay, our code is working correctly. This is not the case. Not getting errors or warnings doesn't mean that our code is working. It means that our code doesn't have a syntax error. But sometimes there is a lot of logical errors that will cause our program to not functioning properly. So make sure that your program is working before moving forward and get help from others. Ask them to check your code and get another eye. They might see something that you are missing. If you followed all of these steps in the hardware and software diagnostic and your project still doesn't work, you can drop us a message or send us an email or contact us via the Q&A board with your problem, a video for your project, some images and your code, and we can help you investigate your problem. I'm here to help you. Thanks for watching this lesson. If you have any question, please ask in the Q&A board. This is Ashraf from Educational Engineering Team. What do you need to become a troubleshooter or an electronic device or electronic board maintenance guy? So, first you need to make a decision to start. And this is the course that will help you do that. Then you need to get the tools needed to become a troubleshooter. After that, you need to know the basic electrical and electronic components, and this will be covered in details plus in practice with some practical video for the most common electrical and electronic components. After that, you'll need to have basic and electrical and electronic circuits analysis skills. And we will also cover this in our course and we will help you analyze any electronic circuit that you have in hand. Then you need to know the repair and maintenance procedure. Once you know that, then you have all the steps necessary to become a professional troubleshooter. Again, we are going to walk you through all of these steps in order to get you up and running in troubleshooting electronic devices and electronic circuits in no time. Thanks for watching this quick intro. This is Ashraf from Educational Engineering Team. Tools needed. In order to become a troubleshooter and in order to fix any electronic device or electronic board, there is a set of tools that you need to have so that you can make your job way much easier. These tools include multimeter, wiring tools, screwdrivers, some miscellaneous tools, and some do-it-yourself tools or kit. We are going to cover all of these in this section, so stay tuned for the next lecture. We are going to cover multimeters in details. Multimeters. Multimeter is a device that most electricians and electronic geeks use to get results or measure voltage, current, and test electronic components. You must buy a multimeter with the following requirements. So the required features, the minimum required features, is that your multimeter must measure up to 50 volt DC. DC stands for direct current, and it can measure up to 250 volt AC. AC stands for alternating current. It must also be able to measure resistance or continuity for testing purposes. You must also get your multimeter with these features. It must be able to measure entry-level current to approximately 250 milliamps. Also be able to measure DC and AC current up to 10 amps. As you can see, these are the two most common types of multimeters. The first one is the analog multimeter, and the second one is the digital multimeter. You can recognize them by the display. As you can see, the digital multimeter has a digital display that displays numbers, while the analog multimeters doesn't have a digital display. Basically have an analog that moves on a scale. So the advantages of analog multimeters is low cost, while the advantages of digital multimeter is that it's easy to read measured value and more accurate readings, because it gives you direct numbers, where in this case you might sometimes have to guess a number between two dashes. Now, when it comes to disadvantages, for the analog multimeter, it's difficult to read measured value, and you need to start at highest range and work way down to suitable range, which means that you don't have a specific range to test your equipment, or there is no automatic adjustment for the analog multimeter. You have to start with the highest possible value and then move down to lower values. The disadvantages of digital multimeter is the high cost, and you need to start at highest range and work way down to suitable range. So these two have the same disadvantage. You need to start at the highest possible range and move down to lower ranges. But this one costs way much more than this one. This one is difficult to read, and this one is easier to read. What we recommend is digital multimeter, because it's way much easier to read, and you don't want to waste time on trying to figure out the value that you are reading. So nowadays, most multimeters comes in digital. Analog multimeters are produced in a way much less volume than before. Now, as you can see, this is a digital multimeter that's used to test this motor, and as you can see, it has a lot of features. The most important one for us here is the auto ranging feature. It's a digital multimeter. It's the third type, but that digital multimeter is way much better than this one. It has a feature called auto ranging, and from its name, auto ranging means that you only need to set the thing that you want to measure. As you can see in this dial, we want to measure volt AC or volt DC, and it will automatically get the result that we want. And this is what auto ranging means. It doesn't have different ranges of values, and we don't need to start at the highest possible value and work our way down. All what we need to do is set the value to thing that we want to measure, which is here volt or ampere or current, and it will do the job for us. And the disadvantage of this is obviously the high cost. It costs way much higher than these two because it has the auto ranging feature, but it saves you a lot of time because using these two you need to start at highest range and work your way down. As you can see here, we have DC, ampere or current. You have to start with the highest value and keep moving down until you reach the range or the required range. While in this one, the third type, which is auto ranging multimeter, all what you need to do is set the quantity that you want to measure, and it will auto range the value to the correct range internally. You don't have to do anything in your dial, and you don't have to adjust anything. So it will save you a lot of time, but again, it will cost you a lot. That's it. We have now a clear idea about the three multimeters: analog multimeters, digital multimeters, and auto-ranging multimeters or auto-ranging digital multimeters. The best one or the most effective one is the auto-ranging digital multimeter because it saves you time by doing the auto-ranging automatically internally. So you don't have to auto-range or start from the highest value and move down to the lowest value, while the other two you need to start at the highest possible value for current or voltage and move your way down to get the correct range. That's it for this lesson. Go and buy the one that fits your budget and your time. What we recommend is auto-ranging multimeter, and we will show you that multimeter in the practical section. Thanks for watching. This is Ashraf from Educational Engineering Team. Wiring tools. In order to deal with wires in electronic maintenance, you need to have a wire cutter and a wire stripper. The wire cutter is also called a side cutter, is usually 5 to 6 inch in size and has a plastic or rubber cushion grip. As you can see in this image, this is a wire cutter, and here we have a cushion grip, and it comes in total 5 or 6 inches when it comes to size, and it's usually used to cut wires to the desired let's say length. And when it comes to wire stripper, there is also another option. You can buy a stripper and a cutter. This one right here is called a wire stripper. It's used to strip off or remove insulation of wires. So as you can see, these two teeth, they close in, and you drag the wire so the insulation material will go away and the cover will stay, and it's adjusted using this screw depending on the wire diameter. These two does the very same job but in different way, and they are very common. This is the most common one and it's very handy, but you need to look for one that is really of high quality, because they tend to get dusty and they are corrupted easily if they are not from a known company. So I recommend going for some top names company when it comes to buying your equipment. Now again, this is the wire cutter and this is the wire stripper. Wire cutter is used to cut wires to a certain length depending on what you need inside your circuit. Wire stripper is used to strip off or remove insulation of wires. That's it. Thanks for watching. This is Educational Engineering Team. Now we are going to talk about electrical master set. As you can see, when it comes to wiring, you need to have a solder or soldering iron or soldering gun. This is the soldering gun, and this is the soldering iron. The gun comes from the original shape of the gun, as you can see here. It has a handle and it has a very gun-like shape. You must buy it with a 30 to 40 watt used in fixing electronic components in circuit boards and splicing wires with small diameters. And if you want, you can get the 60 to 100 watt, which is used to fixing large components such as heatsink and transformers in circuit boards, and for bigger diameter wire splicing. So I recommend having both of them, buying a small one with 30 to 40 watts for fixing small electronic components, and buying another one for much larger components or power circuits, the one that comes with 60 to 100 watt. Or you can buy an adjustable ironing station. They are available in a lot of shapes and from a lot of companies, and they provide from 20 watt up to 200 watt. So that third option might be variable for you, but if you don't want that option, you can either buy a small one if you are working on small electronic boards or circuits, or a large one with 60 to 100 watt if you are working with high currents, high voltage, and large components. Again, the choice is yours and depending on your needs. The one that I have is the adjustable 20 to 250 watt ironing station, and I bought it for a very fair deal. If you are having problem buying any of these components, please send me a message and I'll help you with that. Thanks for watching this lesson. See you next. This is Ashraf from Educational Engineering Team. Screwdrivers. When it comes to screwdriver, the first thing that you need to have is a blade or flat, as you can see in this head, 1/4 or 3/8 inch. It's preferable to have a range of 1/4 up to 3/8 of an inch, and must have at least 4-inch shaft. This is the shaft, and this is the blade or flat head, and you must have a range of them because you might face different screws, and you need to use the right screw with the right head. It also comes with a plastic or rubber grip. As you can see, these two have plastic grip. So this is the first screwdriver type that you need to have. And you'll also need to have a star or Phillips, and this one must have at least 4-inch shaft with also a plastic or rubber hand. The third thing that you need to have is a precision screwdrivers, which are used for smaller screw drives. As you can see, they have very small heads. They are mostly used in small breadboard or electronic circuits, just like the ones available in mobile application or mobile devices or in laptops. You need to have this set of screwdriver with very tiny head and different shapes. They always come together in a box, and they are very commonly available online, so you can get them anywhere. You should also have a set of insulated screwdrivers. As you can see, the shaft is fully insulated using rubber or plastic with a blade flat or a Phillips head. As you can see, these are very useful when you are dealing with high current, high voltage circuits, because you must avoid the possibility of you touching the shaft of the screwdriver when trying to assemble or disassemble a circuit while it's working or while it's powered. So this screwdriver will come in handy, and you will avoid getting shocked by electricity when dealing with these circuits. So have them. They are very necessary, and sometimes in a certain situation you can't avoid dealing with a circuit while it's powered on or why it has power, so you need to be ready for all scenarios. Again, you need to have a flat or a blade screwdriver, Phillips or Star, precision screwdrivers, very small heads, and a set of insulated screwdrivers to protect yourself from electric shock. Now let's talk about a very useful tool. It's pliers. It's used to hold objects such as wires and electronic or electrical components. It comes in many types, the long or the needle nose type. As you can see, this is the long or needle nose type. As you can see, it has a needle shape at the end, and it's very handy for holding objects or wires when I are dealing with electronic components or electronic circuits. There is also the side cutting pliers. As you can see, it has an area here. This area is used as a cutter, and this little head is used to hold components and wires. So this is why it's called a side cutting, because from this side it cuts components or it cuts wires. There is also the slip joint pliers. As you can see here, it has, instead of cutting, it has a slip area where you can hold circular things, and it also has the same head that's here and that's here for holding components and wires, but it does an additional job of holding rounded components or wires or whatever in this area. The most common one is this one. Common ones is this one and this one. This is rarely used or depending on your application. That's it about the pliers. Next we are going to talk about another components that you must have before getting started. Wrench. Wrench is used for electrical and mechanical works. As you can see, there is more than one shape for wrench, and we are going to talk about these three types. They are the most common type. First, there is the open wrench. As you can see, it has two ends and both of them are open. And there is the closed wrench, the same size but a closed ending, as you can see here and here. And there is also the adjustable wrench. As you can see, using this little thing, you can adjust how wide this end is opened or closed. It's like a gear, a small gear that you can move to, let's say, slide this here or close it in the other way, and you can get different sizes of wrenches. So these are the three most common types, and you must have at least one of these three. I usually buy this and this one. They get the job done, but you can get all of them. They come in sizes, as you can see, 14, 17, and they usually start at very low numbers and up to high numbers, and they are sold in a box that has most common wrench sizes inside it, from small to large to larger and so on. Again, if you faced any problem purchasing any of these components, you can reach out to me via messages and I'll be more than happy to help you getting them. Thanks for watching. This is Ashraf from Educational Engineering Team. Oscilloscope. It's previously called an oscillograph and informally known as scope or DSO, which is this digital oscilloscope. It's a type of electronic test instrument that graphically displays varying signals voltage, usually as a two-dimensional plot of one or more signal as a function of time. Other signals such as sound or vibration can be converted to voltage and displayed on this screen. This is an analog oscilloscope, and as you can see, it has voltage divisions and it has different variables that you can play with to get your signal shape, as you can see here. And using oscilloscope, using these wires for different channels, you can connect more than one voltage signal and compare them together. It's one of the most commonly used component in electronic device maintenance and electronic component maintenance. It allows you to display anything and to test any signal and to make sure if there is a signal or not coming out of a device. So depending on the application or the device that you are trying to fix, you can use oscilloscope to make sure that you are getting the right signals as an output from that device. Now, usually if you have an oscilloscope, you must also have a function generator. And the function generator, from its name, is a device that generates different functions depending on your choice. As you can see here, we have a sinusoidal function and a square function. You can click here and it will output that function with the settings that you are applying here. As you can see, it starts from 2 Hz up to 2 megahertz. So you can click on any of these buttons and it will output a sinusoidal signal with 20 kilohertz frequency. You can use that output on your device and see how will it interact with your application. Usually, the function generator is used when we suspect that the input signal from our device isn't working as requested, so we provide the input signal from a function generator to see if our device will output the same signal or not. Again, this is a very high advanced level in fixing and troubleshooting electronic devices, and we are covering it here in our course. If you are buying an oscilloscope, make sure to get the function generator as well. Thanks for watching. This is Ashraf from Educational Engineering Team. Now that we have all the tools needed for our device maintenance, we need to get a clear idea about the basic electronic components. First, we are going to start with passive devices. Passive means devices or components which do not require external source to their operation. The first one in this list is resistors. As you can see in this image, this is how a resistor looks like, and it usually comes with color bands. A resistor is a two-terminal passive component that opposes the flow of current, which means that it reduces the electric current passing through it, and at the same time lowers the voltage levels in a circuit. This component is covered in details in the practical section of this course. The second component is capacitor. This is the physical layout of a capacitor. It's a two-terminal passive component. As you can see, it has 2 legs that is used to store energy. It can be used in a circuit as a smoothing, coupling, and bypass component. Usually, this type of capacitors is called polarized capacitor. It has polarity, and as you can see, this sign and the gray area indicates that this is the negative terminal and this is the positive terminal. Now, if there is no gray area, you can identify the negative terminal. It's the shortest among these 2 terminals. And another type is the ceramic capacitor. It comes without polarity and it's like a circle. Again, this component is covered in depth in the practical section at the end of this course. Now, the third component is inductor. As you can see, this is an inductor. It's a it has two terminals, passive component that store energy in the form of magnetic field. It is used in circuits as a choke and reactor in RF receiver and transmitter circuits. So, in any radio frequency circuit, in any FM or AM circuit that transmit or receive radio signals, you will find that inductor. And it's the third type in our passive components. Again, all of these components are covered in the practical section of this course in details, but this was like a quick overview of these components. Next, we are going to talk about the active components, but that's it for this lesson. Thanks for watching. This is Ashraf from Educational Engineering Team. Now let's talk about the active devices. Active devices are devices or components which requires external source to their operation. The first one in our list is the diode. A diode is a two-terminal p-n junction device that allows the flow of current only in one direction. It may come in many shapes. As you can see, this is the original shape. It has a gray line here indicating that this is the negative terminal and this is the positive terminal. The positive terminal is called anode, as in this schematic, and the negative terminal is called cathode. This is called a rectifier diode. This diode rectifier circuits of power supply units. The second shape of this diode is this physical shape. It's called Zener diode, and it has the very same symbol but with two, as you can see, dashes. This is the anode and this is the cathode, and its function is voltage regulator in power supply units. The third most common one is the LED or light emitting diode. This is the symbol for the LED. It's the same as this symbol but has two arrows going out of this diode, which means that this will emit light and light will get out of this diode once current passes through it. Calculators display, TV, mobile phone displays, and any indicator circuit uses LED to indicate a specific state, just like turn on and turn off. So these are the three shapes, and they are very common components in any electronic circuit. So each circuit has at least one diode and one LED. Next, we are going to cover transistors, and it's also a very common component in electronic circuits. Thanks for watching. Keep in mind that these are the three physical shapes for rectifier diode, Zener diode, and LED, which are basically three different shapes of diode. Now to the second element in our electrical and electronic components. It's also an active element. It's called a transistor. Transistor is a three-terminal active component that is used mainly in boosting or amplifying electrical signals, both AF and RF ranges. Other application of transistor includes using it as a switch or amplifier for amplifying voltage or current signals. Now, as you can see, this is the physical shape for transistor, and high power, high current, and voltage transistors comes in this shape. This one is called a BJT transistor or bipolar junction transistor. It's for current control devices, and it comes in NPN or PNP types. Its main function is voltage regulation, audio frequency amplification, and this is the symbol for that type of transistor, and this is the physical layout. The second most common type is field effect transistor or in short, it's called FET. It's for voltage control devices, and it comes in two types, N channel and P channel. This is the electrical symbol, and this is the physical layout. It's basically used in audio and radio frequency amplification and in USB or universal voltage AC to DC or DC to AC circuits, and it's very common component as well. These two elements are very important, and you need to know the main working principle for each of them in order to be able to identify if there is any fault in them. We did cover this in the practical section at the end of this course, so if you don't already know what is a transistor or how it works, you can hit there and see for yourself how to test a transistor, how to check if that transistor is working or not, and how different types of transistors work. Again, there is two main types, BJT and FET. The BJT is for current controlled devices. The FET is for voltage controlled devices, and these are the rest of information that you need. Basically, it consists of collector, base, and emitter. This one has a gate, drain, and source. Thanks for watching this lesson. Next, we are going to talk about some of the common electronic and electrical components. But that's it for this lesson. If you have any question, please ask in the Q&A board. Hello and welcome. In this lesson, we are going to cover some of the most common components in electronic and electrical applications. The first one is the fuse. As you can see, the fuse is a device that limits the amount of current that can be drawn by an electric circuit by opening or blowing or melting when the current exceeds a preset limit. As you can see, it usually comes in this shape. It has two metal pieces, and in the middle there is a plastic or glass piece, and there is usually a thin copper wire between these two pieces. That copper wire will blow in or melt when it faces high current than it can handle. This is the symbol for that element, and it's one of the most commonly used elements in the input circuit in any device, especially in power circuits. Next is the bulb. Bulb is a very common item. It serves as the load. It turns the electrical energy into light, and you might have one in your room right now. This is how it looks. And now we have LED bulbs. This is a tungsten lamp that consumes a lot of energy to convert a current or electricity into light. Now we have LED. It's more power efficient, and it doesn't have helium or gas inside it. This is the electric symbol. Then we have the power cord or plug. Usually this will have a line, a neutral, and an earth terminal. And as you can see here, we have a fuse on the line terminal to make sure that you are protecting the device from high currents. And that cord or plug will have an insulation. So it's basically a cable. This is the insulation material, and here we have three cables or three wires, line, earth, and a neutral. They are placed depending on each of them, depending on the name, and they comes in different colors, usually brown, blue, and yellow for earth. As you can see, brown, yellow, and blue, and they are used everywhere. Any of your devices, if you want to connect it to electricity or to a plug, you need to use that power cord or plug to connect it. So it's used for temporarily connects an appliance or an equipment to the mains electricity supply via wall socket or an extension cord. Next we have switches. This is how a physical switch will look like, and this is the electrical symbol. These are necessary to turn the electrical circuit on or off. And we have the connecting wires. They comes in many shapes. And in circuits, if you have a dot between two wires, this means that these two wires are connected. If you have this sign, this means that these two wires are not connected. And wires are usually used to create a complete circuit path through which current flow from the source going to the circuit load. Now, what about transformers? This is how transformer look, and this is the electrical symbol. Transformers are used for protection of appliance and equipment connected to AC power supplies. It can change the electrical voltage or current from one level to another. So let's say that we have a device that works on 12 volt and we are getting 220 volt from the power socket. A transformer is the device that is going to step down the voltage from 220 to 12 volts. So this is what it does. These are the main components in any electric and electronic circuits, and this is it. Now what you need to do next is know how to test each of these components. This is the thing that we are going to cover in the next lesson. Now let's talk about bulb or lamp. The physical appearance of busted or burnt out bulb is like this. If it is a tungsten bulb, you can see that there is a wire broken inside it. This broken wire means that this lamp is no longer working. If you have another type of lamp and you want to know if it is working or not, you can simply hook it up to the power and see for yourself if it is working or not. This is a 12 volt lamp, as you can see. So if you have connected 12 volts to its terminal, and if it did light, this means that it's working, otherwise it's not. Or in some cases, you can use the continuity test in your digital multimeter. The busted bulb will give you infinite resistance, which means that it's open and there is no continuity. While the good bulb will give you low resistance, but not zero, and in most cases it will give you a beep or buzzer when you are trying this with the continuity test or continuity function in your digital multimeter, just like the one that we explained in the previous lesson. Now if it is connected, it will give you a beep. If it is not, it won't give you anything. Or if you use the resistance measurement test, it will give you a very low resistance. If it gives you a high infinite resistance, this means that the bulb is broken. Hello and welcome to this new lesson in which we are going to cover switch testing. A switch is basically an element that allows current to flow, to continue, or to connect a circuit elements together. Now, it comes in different shapes, as you can see in this image, and if you want to test it using a multimeter, using the continuity test on switch means that the multimeter will beep when you are connecting your probes of the multimeter to the two terminals of the switch. If you are connecting them and you switch off your switch, it will not beep. This way you know that your switch is working just fine. Now if it does beep in both way, in the on state and off state, it means that there is a problem with that switch. And if it does not beep at all, even if it was on, it means that it's not working properly. So it's very easy, very straightforward, very similar to the fuse testing. So that's it. Thanks for watching this lesson. This is Ashraf from Educational Engineering Team. Hello and welcome. Now let's talk about how to test a transformer. As you can see, transformer comes in different shapes, but they all follow the very same simple principle. transformers are wires that have resistance. So no matter how many terminals there is, if there is a resistance between each two pins, depending on the type of transformer, it means that the transformer is working. Now, depending on how high or low this transistor is, you can identify the primary and secondary coils, or you can identify that a coil is burned out. Now, the first step is meter indication for testing a good transformer. The primary winding and secondary winding can be tested as follows. You need to set your multimeter to the resistance measuring for the indicator. Now place the two probes on these two terminals of the transformer, or the terminals that you think are the primary terminals. Now the meter deflection indicating high resistance, this means that this is the primary winding. Now if the meter deflection indicates low resistance, this means that this is the secondary winding. So whenever you are testing to find out which are the primary and which are the secondary, the ones with the high resistance are the primary winding, and the ones with the low resistance are the secondary winding. Now, if you want to know if the transformer windings, primary or secondary, are shorted or open, you can use the simple test of resistance. If the meter deflection indicating zero resistance in the meter, this means that our transformer is shorted. Now, if no meter deflection indicating infinite resistance, so if the resistance went very high to the maximum at the analog multimeter, or the highest or infinite value in the digital multimeter, this means that there is a cut in our transformer winding. So how do you know which are the terminals for primary and secondary? Usually by copying the transformer name or number and finding this number and looking up on Google for the datasheet for that specific transformer. You can easily identify these numbered terminals and know which are for the primary and which are for the secondary. Now, next we are going to cover the resistor, but for now what I need you to know is that every transformer has a different type of test, but all depends on a very basic truth, which is a transformer is basically a wire that has a resistance. So if the resistance is too high, this means that this is the primary winding, and if it is too low, this means that it is a secondary winding. If it is zero resistance, this means that that specific winding is shorted. If it is infinite resistance or infinite resistance, it means that this winding is open. So this is the overall. Usually what I do is look up the transformer online to know the terminals and label them with numbers or letters, then start the test by identifying the primary and the secondary, then move on to test if there is a shorted or open winding inside that transformer. I will add more resources on how to test a transformer to this section, but that's it for now. Thanks for watching. This is Ashraf from Educational Engineering Team. Hello and welcome. In this lesson we are going to talk about resistors and how you can identify if a resistor is in good shape or if it is broken. Now, if it is a good resistor, the measured value must be within the range of the rated value. The measured value using an ohm meter or a multimeter. The measured value using an ohm meter or a multimeter is a way to determine the resistor value in a circuit. Another way is using the color band. So we can determine the resistance of the resistor using the resistor color coding. As you can see, each of these colors indicate something. So if the color came in the first digit, as you can see, in a 4-band resistor, 1, 2, 3, 4, or in a 5-band resistor, each color means something. If black was the first digit, this means that the first value is 0. If black is the second digit, then this means that the second value is 0. Same for third, and here we have a multiplier and tolerance. So let's say that we have this resistor. Yellow means number 4, so we can write 4 up here, as you can see here. The second color is purple, it has number 7, so we are going to write 7 here. The third digit here, in this case, is the multiplier. In a 4-band color code, we have 2 digits and a multiplier and a tolerance value. In a 5 bands, we have 3 digits, a multiplier, and a tolerance value. So the third digit is not usable here in the 4-band code. So we are going to use the multiplier, and the orange means 1000. So 3 zeros. And the tolerance is this color, which is gold, and it will be plus or minus 5%. So it will be 74 or 47 kilo, because we have 3 zeros, ohm, with a tolerance of plus 5%. Now in the 5 band, we will do the same thing. The green is number 5, so we write 5 down here. The brown is number 1, as you can see here, so we write 1 down here. And since it's 5 band code, we will use the third digit, which is black, and it will be 0. And the red for the multiplier means 100, so we will add 2 zeros. And here we have a brown, which means 1% tolerance, and we will add 1% tolerance, so it will be 51. 3 zeros means kilo ohm. That's it. This is how to use color coding to identify the resistor value, and this is the best way to identify a resistor value inside a board without having to remove it. Now, to know if that resistance is working or not, you have to measure the color using the color code. Then you have to break out one of the 2 legs for that resistor from your board and measure it using a digital multimeter. And if these 2 values match, the color coding value and the digital multimeter value, if there was a match between them, this means that this resistor is working properly and there is no problem in it. So what you need to know is that you need to find the resistor value using the color code, and you need to match it with the digital multimeter value. If these 2 are the same, it means that the resistor is working just fine. Otherwise, it means that you have a problem and you need to fix that problem. Now, one thing that you need to know is that you can't measure the resistance using a digital multimeter while the resistor is still on board. So you have to disassemble or desolder one of the 2 terminals of that resistor so that you can measure it correctly, because sometimes when you measure it while it's still on board, you might end up measuring it with other components connected to it, parallel or serial. So this will cause a reading error, and to avoid this, we usually recommend desoldering one of these 2 terminals and removing them from the board, and then you can test it or measure it using your digital multimeter. Now, in order to cover this in more details, these are some examples for a physical appearance of bad, effective or defective resistor. Now, as you can see, this is how a resistor looks when it is burned out completely. This is a slight burnout, but you can still recognize the coloring. Here you can't recognize anything. So if you saw a resistor that looks like this in a board, this means that this resistor is broken and you have to replace it. So in order to measure a resistor using or test a resistor using a digital multimeter, you might end up with three results: open, shorted, or change value. Open meter deflection indicates infinite resistance reading. This means that that resistor is broken entirely and these two terminals are no longer connected together. Shorted meter deflection indicates zero resistance reading. This means that this resistor is now like a wire connected and it doesn't have any value. It's just zero resistance, so it's like shorting two terminals, a positive and negative, and connecting them directly together. Now, the third but rarely happen incident is change in a resistance value. Rare defect of resistor, measured value is not within the range of the rated value. So if it is a 10 kilo ohm resistor, you might measure it and read 5 kilo ohm resistor. This is not a very common case. Usually it's either open or shorted, but it might happen. It's very rare, but it might happen, so you need to know that it's there. You need to make sure that before testing a resistance, you desolder one of these two terminals from the circuit, or you can desolder the whole resistance and test it outside, then brought it back or resolder it to the board. That's it for this lesson. If you have any questions regarding the resistance, please ask in the Q&A board. Thanks for watching. This is Ashraf from Educational Engineering Team. Troubleshooting and repair procedures. Now, before moving forward in this section, there are some safety concerns that I need to cover to make sure that you understand what you are doing and you are not endangering yourself or others. First, you need to contact professionals and qualified servicemen for equipment that poses risk. What do I mean by this? This is a simple and straightforward sentence. That means if there is an equipment or a device or a board that is in a risk environment, a chemical or high electricity, high voltage, high power environment that you are not trained to deal with, you should call someone who is trained and who can be in that environment and interact with things. You might end up killing yourself if you try to fix something in an uncontrolled environment that has chemical reactions and things that might hurt your life. The next thing that you need to make sure of is that you have proper tools before moving forward. Not having proper tools might end up killing you. We already mentioned that you need a screwdriver with an insulated shaft when you are dealing with high current or high voltage screws, because you might end up touching the shaft and killing yourself if it wasn't isolated. And using that very same concept, you can apply this to all of other equipments. Any equipment that you use must be the right equipment that is used for the right job. Don't use or try to use anything that you have in hand, because this will hurt you and will hurt the equipment that you are trying to deal with. The next step is instruments must be well maintained and correctly calibrated. Some instruments needs professional calibration by an expert in the field. So if you are dealing with a chemical equipment board, you must make sure that someone from the same field is there with you to help you know what are the right adjustment, what are the right values for the calibration in order for this board to work correctly. When dealing with voltage, you need to make sure that you are disconnecting or isolating power before moving forward in testing and trying to figure out what's happening. Also, make sure that you are using insulated gloves and tools, as we already mentioned. Make sure that you are using GFCIS, which is Ground Fault Circuit Interpreter. This device will make sure that if there were electricity, you won't get killed in the process. It will do its best to make sure that you stay alive if something happened while you are dealing with that circuit. So it's like a ground circuit breaker, but you are holding it in your hand and it's saving your life while you are working on the device that you are doing the maintenance for. Make sure to have it and make sure to use it correctly to make sure that it will help you finish the job without getting killed. Again, here we are dealing with devices that has power, and when you are doing this, you must make sure that you stay alive. Your life matters more than that device, so don't get foolish and just get to it and start unscrewing screws and just getting the job done, because you might end up killing yourself or killing someone else. These are the safety concerns that you need to make sure of when you are dealing with electric and electronic equipments, and you are the troubleshooter here. You have to be safe and to feel safe in the environment so that you can do your best solving the issue. Thanks for watching this. This is Ashraf from Educational Engineering. Main concerns. The effective and efficient working condition of a certain laboratory equipment depends on the following 4 features: maintenance, servicing, troubleshooting, and repair. Now, the first thing that we are going to cover is the maintenance. Maintenance is a continuous process. It must include both the hardware and the software maintenance. The hardware maintenance includes cleaning, dusting, and making everything crisp clean, maintaining prescribed level of parameters such as electrical, environmental, and other parameters depending on the type of board, device, or system. The software maintenance includes reinstallation or uninstallation of the software, upgrading the software if there is any new version comes up. So again, maintenance is a continuous process and it's a must in every device or board that you are using or that you are dealing with. Sometimes the problem with the device is a bad software. Sometimes it's dust all over the board, causing short or causing the board to function abnormally. So you need to make sure that you avoid all of these first before going to the troubleshooting. Now, the second step in main concerns is servicing. Servicing is mainly associated with the hardware parts of the equipment. It includes checkups, repairs, and updating of all physical components. Servicing has a lot of steps that we can summarize as follow. The first step is uninstall. Uninstall all physical components starting from power connections. Then move to dust. Dust cleaning is a very important part, so you need to clean the dust from the components. After that, you need to move to performing a visual check or electronic check as required. Then reinstall all components carefully and properly. After that, you need to check for loose wiring or cracked cables. Again, you need to check if any jumper is missing. If required, replace it with a new one. If there is a physical damage of peripherals and you need to replace it if needed. If there isn't, you need to leave the peripherals as it is. After that, you need to make sure that you are tighten all internal and external connections. Then you can switch on the power supply and observe if the device is functioning correctly before moving to the troubleshooting phase. Hello and welcome. Now we are talking about the third step in main concerns, which is troubleshooting. Troubleshooting means detection and rectification of faults in the equipment. After troubleshooting, you can move on to repairing, which means repairing or rectifying the problem in the hardware or software. It is an essential part of troubleshooting. Repairing may also include replacement of a component. Now, there is a 6-step procedure for troubleshooting a problem, which is a standardized approach towards electronic troubleshooting and maintenance. These 6 steps will be discussed in order to achieve proper solution for your problem. The first step is symptom recognition. Symptom recognition includes determining if the equipment is functioning as designed. Each equipment or each board has a specific way or a specific input and a specific output. You need to check and know if there is a problem with these outputs, if they are out of range, if there isn't output at all. A trouble symptom is an indicator of malfunction. Use your sense of sight and hearing. Do you hear anything that's not usual? Do you see anything that's broken, burned out, or blown? If you do, you need to take proper measurement. This is the first step in troubleshooting. Next, you need to do symptom elaboration. You need to ask yourself what fault is probably causing the specific symptoms. Symptom elaboration requires an evaluation of all observed displays. You need to make sure that indications must be evaluated in relation to each other as well as the overall operation. Record information observed. Use a paper. For example, how did each control affect an associated meter or other indicators? Think about the information before jumping to a conclusion. Write down everything, try different output and try out different input and observe the output. Do you see anything that's not usual? Do you see any change or spike? Do you see something that's broken? Observe, write down, don't do anything. At this point, you are only just studying the whole problem and trying to figure out what's happening. Now, you need to list probable faulty functions. You need to divide the equipment into functional areas in order to save troubleshooting steps. Use functional block diagrams, or in short FBD, to show the functional areas of an equipment, as well the detailed functions, levels of inputs and outputs parameter for voltage and current. Making that diagram will save you a lot of time. Make sure to state the input and the expected output for each block. Then start measuring. Next, you need to localize the faulty function. Now that you have a block diagram with all the required functions, you need to start isolating the functional area that has an indication of malfunction. Knowledge, skill, and proper test equipment should now be used to isolate the fault functional area. After doing this, now you have a clear idea what are the areas that have fault or problem and what are the areas that are functioning properly. Localizing the trouble of the circuit. First, you need to isolate the circuit within the fault unit. More extensive troubleshooting is now required within the identified fault unit. Look for improper voltages, improper waveforms using oscilloscope, obvious component overheating, or components that are blowing out. So use your eye, use your nose to smell, and use your hearing. Use your ability to identify problems from their physical appearance. If nothing is shown, you need to start using your multimeter, oscilloscope to start testing each component as we explained previously. Isolate the defective circuit group. After this, you need to do failure analysis. Step 1 and 2 were used to recognize, verify, and obtain descriptive information. Step 3 in our process allowed you to make a logical selection of the logical fault unit. Step 4 provided for simple input-output test and localized the faulty functions. Step 5 localized the fault to the circuit within the fault unit. Step 6 will involve the actual replacement or repair of faulty circuit components. Now that you have a clear idea what's the circuit that has the problem, you can replace any faulty component inside it, or you can replace the whole board, depending on the type of this particular equipment. This is it. If you follow these 4 or these 6 steps, you will be able to make a diagram for your equipment or your board with inputs and outputs, and you will be able to separate each of these functions into a separated block diagram, and finally you will be able to identify the board that has the problem and replace it or fix it depending on your skills. That's it for the failure analysis. If you follow these steps one by one, you should be at the end of step 6 in the process of replacing or making the device work. Thanks for watching. This is Asher from Educational Engineering Team. Hello again. Today we will talk about the components of electricity. We will talk about voltage, current, resistance, types of currents, AC and DC, and different types of circuits, close, open, and short. Let's start by talking about voltage, current, and resistance. As you can see in this image, we can use water to visualize how electricity works. As you can see here, water flowing through a house is a good way to look at electricity. Water is like electrons in a wire. Flowing electrons is called current. So this water that comes out of this pipe is, you must imagine it as electronic or electrons. Pressure is the force pushing water through a house. Voltage is the force pushing electrons through the wire. So we have electrons for water, voltage for pressure or water pressure. Friction again is the whole walls slows the flow of water. So resistance is the force that slows the flow of electrons. So when the resistance increase, it will decrease the whole amount of water coming out of the pipe. If we increase the pressure forcing the water through the house by opening up the spigot, the water flows faster and squares further. The opposite happens when we reduce the pressure. The water flows slowly, right down to a trickle. In electricity, the force pushing electrons through the wire, current, is voltage. If the voltage is increased, more current flow. If the voltage is decreased, less current flow. Now imagine keeping the pressure constant and visualize what happens when we change the amount of water available to flow through the house. If there is lots of water, the water will flow out at full force. If there is limited water, no matter how hard you push, the water will only flow out at small trickle. In electricity, if there is ample current available, it will flow through the wire at full capacity. If you limit somehow the amount of current, then the current will only flow at a reduced rate. Finally, imagine what happened if you kept the pressure and the amount of water available constant, but restricted the diameter of the hose, like putting your finger over the end. The restriction prevents the all water from coming out, but the water that does come out comes out with greater force. It will squirt further. Also, the water behind the restriction actually slows way down to wait its turn to go out of the restricted hole. The same thing would happen if the interior wall of the house was made very, very rough. The water molecules would run into the rough surface and slow down. There is very much like friction. In electricity, the current does not flow through a wire without running into something along the way. There is always some friction, but in electricity, that friction is called resistance. When resistance goes up, the amount of current flow goes down. When resistance goes down, the amount of current flow goes up. Now, you can examine that yourself with a water pipe and test different concepts, but this is a thing that we should mention at the beginning of our course so that you know what are electrons, what is voltage, what is resistance, and we tried to make a real life example using water. Now let's look at this image here to summarize what we have learned. As you can see in A, we have low pressure, so small amount of water. Low pressure and small amount of water is coming in A, while in B there is high pressure, large amount of water. As you can see, the water will go further since the pressure here is high, while in case of large diameter pipe, as you can see, this diameter is way much larger than this, then large amount of water will come out. Here the pressure is constant, but the amount of water that came out of here is way much more. This means that this pipe has low resistance in electricity terms, and this one these two has high resistance since they have a small diameter, while this one have high resistance. This is the pipe example for voltage, current, and resistance. I hope that you got the idea. If you have any question, please ask in the Q&A dashboard. Thanks for watching. Hello again. Now let's talk about type of current. There are two types of current. The type is determined only by the direction the current flows through a conductor. The first type is direct current, or DC, flows in only one direction, negative toward positive pole of source. The second type is alternating current, flows back and forth because the poles of the source alternate between positive and negative. This means that if the current alternates from flowing in one direction 1 minute and then reversing to the other direction the next moment, the current is alternating current. Now let's look at this schematic. As you can see, this schematic shows AC current vocabulary. This is the maximum positive value, and this is the maximum negative value, this line and this line. This is the value to be measured, voltage or current. As you can see, starting from 0, it will go in the positive direction, then it will go in the negative direction. This means that this is an AC current, since it goes in both directions, positive and negative. If it only in the positive direction, then it will be a DC current. Let's look at some terms here. The point from here, A to B, is called one cycle. This is one cycle, as you can see.
half of it in the negative direction and the other half in the positive direction. We can also call the point from 0 to this point a cycle or one cycle. This axis is the time axis, and as you can see, this is the distance traveled in one cycle, which is called wavelength. These are the basic concepts that you need to understand about AC and DC in currents and voltage. They are very much the same. In DC it will be a constant value in one direction, while in AC it will be a value that alternate between positive and negative direction. Thanks for watching. See you next lesson, in which we will talk about circuits. Hello. Now let's talk about circuits. A circuit is a path for current to flow. There is 3 basic kinds of circuit: open, closed, and short. Open circuits, in which the path is broken and interrupts current flow. Closed circuit is in which the path is complete and current flows where it is intended. While short circuit, the path is corrupted in some way and current does not flow where it is intended. Let's look at this schematic. As you can see here, we have 3 circuits, A, B, and C. In A, this is a closed circuit. As you can see, this is a battery and this is a bulb or bulb light. 2 wires are connected directly to the battery and current flows correctly. Now if you look at this schematic, the battery and the bulb are connected but in a messed up manner, so broken insulation allows wire to touch, producing a short circuit. These 2 wires are not insulated, so copper appears, and if 2 wires are connected together in that circuit, this means that there is a short circuit here and current won't flow. In this circuit we can see that there is a battery and a bulb, but one of the 2 lines is broken here. Breaking wire produce open circuit. That's it for types of circuits. In the next lesson we will talk about volt ohm meter basics and we will go in depth. Thanks for watching. Hello and welcome to this new lesson in which I will talk about digital multimeter. This is a quick introduction to this device. The one that I will be showing you is Unity, as you can see. Okay, let me show you a few things. Now, this device is basically used for showing on this LCD, showing digital readings for volt, ohm, ampere, and other stuff that I will talk about now. So let's take a quick introduction to the basic components here. Now, if you looked at the bottom here, you will find there is a COM, which is the common. Usually we connect the black wire to this opening or this hole, and here we have like 3 openings, each one with the type of the thing that it's used for measuring. So this one is used for measuring 10 amp max. So 10 amp max, if you placed any device that will consume more than 10 amp, the fuse will be blown. So this one is used to measure current in milliamps, and it's used also for measuring the temperature in Celsius. This opening is used for measuring volt, ohm, the diode, and the hertz. As you can see, each of these is used for a certain thing. You can't use it for any other thing. Now let's move up here. As you can see, we have this LCD display. It's used for displaying the results, and if you take a good look at it, you will find that it has a lot of things. Now we have the power button here. If you click on that button, the display will turn on. We have the hold button here. If you click the power button and took a reading, then press the hold button, the reading will remain on this LCD display. It won't move. As you can see, it's stating hold. Okay, now this is a quick introduction. Here in the back we have like something that can help keeping this up if you want to use it and to take readings. Now let's take a quick look at this dial. As you can see, you can move it away to choose different things. Now if we turn on the power, let's start from the bottom. Let's start with the ampere. As you can see here, we can measure 20 milliampere, 200 milliampere up to 10 ampere AC. As you can see, A with this sine wave shape means this will be used for AC readings. And if we moved here from 10 to 100 milli and 20 milliampere DC, this constant line means DC, so these three will be used for DC readings. And if you want to measure the hertz, we will move this. It will measure up to 20 kilohertz. If we want to measure the capacitance, we can measure from 2 nanofarad to 200 microfarad. As you can see, you can change the reading from here. If you want to measure the temperature, you can choose this one. If you want to measure the other readings such as diode or connectivity, you can choose from here. Let's move on. This is the ohm reading. Okay, let me just, what you can see here, we have starting from 200 ohm, 2 kilo, 20 kilo, 200 kilo, 2 mega, 20 mega, and 200 mega ohm. So all of these can be used for reading the resistance. Next we have these readings for volt. As you can see, there's a constant line, so volt DC, starting from 200 milli to 20, 200 and 1000 volt. Here is the same. We have volt with the sine wave shape, which means AC volt, 220, 200 and 750 volt AC. So you just need to move the dial to this point so that you can take the readings in volts, and it will adjust itself or the LCD screen. Now one thing that you need to know before moving on is that when you choose the reading from here, if you want to measure volt AC, you have to connect the wire. You have to look here. Here we have the volt, so I will connect the red wire here and the common here. Then I will measure volt. If I want to measure ampere, let's move. I will move to ampere. As you can see here, 10 amp DC. And since I'm measuring 10 amp, I will put the red wire here and the black wire here. These are the wires that I'm talking about. Let me show you. These are the two wires. This is the red and this is the black wire. The black is usually connected to the common, and the red is usually connected to one of these three, depending on the dial movement. So if I want to measure hertz here, as you can see, I will go and choose hertz from here. That's it. Make sure that before moving this from one to another, you turn off that LCD display, because if these two wires were connected to something and you move, let's say, from hertz to ampere, it might break your digital multimeter. So make sure to turn off before moving this wire from one type of reading to another. That was a quick introduction to how to use a digital multimeter to measure different things. We will talk in more details about resistors, capacitors, inductors, and other things, but that's it for now. If you have any question, please ask in the Q&A board. Thanks for watching. This is Educational Engineering Team.
Hello and welcome. Today we will talk about volt-ohm meter basics. Measuring electricity. The common function for volt-ohm meters is measuring voltage, AC and DC, and different ranges, measuring current AC and DC in different ranges, and measuring resistance in ranges and continuity, in addition to measuring semiconductor performance, transistors and diodes, in addition to capacitors. As you can see in this slide, this is
one of the basic ammeters or volt ohm meter. This is the meter reading digits, and these are the scaling DC voltage scale. As you can see here, there is a V plus a sign here. This sign means DC. AC voltage scale, as you can see, V letter plus an AC sign or sinusoidal sign. Function selection, as you can see, this probe is used to choose any function from these. It will rotate in any direction. Function selection, this one is for function selection. Probes, these two probes are used to measure the components. These are two wires that are connected to the components to be measured. And as you can see, this is a very basic meter. Now let's look about other components that this meter might have. As you can see here, there is DC current low. As you can see here, this measures from 200 micro ampere to 200 milliampere. This is for small DC current. This is for large or high DC currents, 10 amps. This is the diode checker. As you can see, this there is a diode drawn here, and this is the transistor checker. This is for resistance measuring, as you can see, starting from 200 ohm to 2000 kilo ohm. You can choose any of these to measure them. And I think that this is the most common type volt ohm meters. Other type might have other functions, and depending on how much your budget is, you can choose any. As you can see, there is 3 probes here. This one is for measuring ampere in DC, and this one is for measuring voltage or small currents, and this is the common. It must be connected all the time. This one is moving from here to here depending on the amount that I want to read. And as you can see, it says 10A DC, which means that this will be used to measure the ampere or the current in DC, while this one is used to measure voltage, resistance, and the current in milliampere. So you have to be careful in dealing with these 3 probes. You have to connect each one to the right place, as mentioned here. Now we won't use it in practical. We will use it in the experiment sections, but you need to understand how it works and how to use it. Let's see the volt ohm meter basics. We mentioned earlier that it will be used to measure voltage type, scaling, safety, physical, and equipment. For measuring current type, scaling, plus safety. Now you have to be careful using a multimeter or a volt ohm meter. You can also measure resistance and do different scaling. We will do this in practice or in practical experiment next. But now you are ready to actually use this meter, and we will cover these 3 functions. I will show you how to measure voltage, then how to measure current, then how to measure resistance in slides or theoretical manner at first, then in a practical manner. That's it for now. Thanks for watching. Measuring voltage. Voltage type, there is 2 types of voltage, which is DC and AC, and we did mention the difference between them earlier. When measuring voltage, the meter probes are placed across the voltage source. The volt ohm meter uses 2 separate functions and ranges to measure DC and AC. Because AC is constantly changing waveform, measuring AC voltage is not a simple matter. This volt ohm meter measures base weight RMS voltage. And we must mention that when measuring voltage, the volt ohm meter is used to sample the voltage across the source, which is different than when measuring current, where the current in the circuit must flow through the volt ohm meter to be measured. This makes it far easier to measure voltage in a circuit because the operator can simply place the probes across the component as it is wired in the circuit. While in measuring current, the operator must physically interrupt the circuit, unsolder and connect, and insert the volt ohm meter into the circuit. So you might have to unsolder a component, remove its connection so that you can measure the current flowing through it. We must point out that the two voltage measurement ranges, one for DC and the other for DC, and we will see how to measure both of these. Now let's look at this digital multimeter or volt ohm meter. We must scale set to highest predictable. If we are measuring resistance and we don't know how much that resistance is, we must put the scale at the highest value. Now the probes must be inserted into the jacks, as you can see here, and we must know the voltage polarity. As you can see in these two batteries, this side is the positive and this battery, this side is the positive. So we must place the positive probe here and the negative probe here to better measure the voltage. Now let's look at how we can measure that battery voltage. Set up the volt ohm meter on 600 volt DC. As you can see here, we are pointing at 600 volt DC since this is a DC battery. We must touch red probe to plus, as in here. As you can see, this is the red probe, and touch black probe to negative, as you can see here. Then we must read the voltage to the nearest 1 volt. As you can see here, this is a 9 volt battery, so it's displaying 9. And you can try this at home. I'm sure that you have a multimeter and a battery. This is a very simple technique, and we must be sure of what we choose. I'm measuring a DC current here, so I choose volt DC. If I'm measuring AC, I must choose volt AC. So you must take a very good care of this setup before start measuring anything. And now let's touch the probe to the negative battery, the red probe. As you can see here, we are reversing the connection, and we touch the black probe to the positive side. We are reversing the connection, and we read the voltage to the nearest 1 volt. As you can see, there is a minus sign here, which shows that the volt is negative since we are measuring it in the reverse manner. And the purpose of this exercise is to show that the volt ohm meter can tell the difference between negative and positive voltages. We must point out that some volt ohm meter, particularly analog type, will not be as forgiving, that putting the probes on reverse voltage can damage the meter. So if you have an analog volt ohm meter, you shouldn't try this. Just place the positive on the positive side and the negative on the negative side. Now let's see if we are to measure another to take another example using a voltage scale that is closer to the actual voltage, showing an improvement in the resolution. So if we know that this is a 9 volt battery, why choosing a 600 volt scale? Or if we know that this battery will measure a volt between 1 and 20, why choosing 600? This will decrease the resolution significantly. In this case, we know that this is a 9 volt battery, so we are adjusting the scale. Now set up your volt ohm meter on 200 volt DC scale. Touch red probe to the positive and touch black probe to the negative. Let's read the voltage to the nearest 0.1 volt, not 1 volt. As you can see, 9.5 volt, which means that we have a way much higher resolution. There is a 0 here. Now if we did another adjustment and placed the volt ohm meter in the 200 volt DC scale, as you can see here. Now let's touch the red probe to the positive and the black probe to the negative. and read the voltage to the nearest 0.01 volt. As you can see here, 9.5, and the 0 came here, unlike in the previous example. As you can see, the 0 was here, now it's here, so we have a way much higher resolution. This is a very good example that you must at least have a clue how much the voltage should be or in what range, so that you can get a good result. Now let's look at this 1.5 volt battery example. Set up the volt ohm meter to 20 volt DC. Touch the red probe and the black probe in the positive and negative direction. Using a 1.5 volt battery, read the voltage to the nearest 0.01 volt. As you can see, the reading is 1.52. The 2 here means that we have a very high resolution, and that we can measure in millivolt range, not just volt range. Now let's see the next example, in which we will look at battery, but in the millivolt scale. Now let's set the volt ohm meter to 200 millivolt scale. This scale is reading 2000 millivolt or 2 volts. Touch the red probe to the positive and the black probe to the negative. Okay, now we are using the 2000 millivolt scale. We are actually using the 2 volt scale because 2000 millivolt is the same as 2 volts, but because the display is in millivolt, there is no decimal point in this case. A reading of 1527 millivolt is the same as 1.527 volt. So as you can see here, we are using the millivolt range, and we are setting it here in the volt ohm meter. As you can see now, in this 1.5 volt battery, we can read the voltage to nearest 0.001 volt, and the reading is given as 1500 to 27 volt. It's equal to 1.527 volt. So it's the same, but you just make the resolution a way much higher. Now let's see if we want to look at the other example. In this example, we are setting our voltmeter on 2000 millivolt DC scale, and we are touching the red probe with the positive and the negative probe with the negative side. We are using a 9 volt battery, and this is clearly an over voltage situation. Note the reading, it's 1. So you must know what happens if you use a scale that is too low for the voltage being measured. As long as you do not exceed the maximum voltage value of the meter, in this case 600 volt, there will be no physical damage to the meter. The meter indicates an over voltage situation by displaying a single digit 1 at the far left. This overage indication is consistent with the or the other functions to be looked at later. So a 1 means that we have over voltage and we didn't choose the right resolution. Now let's talk about safety in measuring. When measuring voltage, the voltage being measured is exposed to the operator and flowing through the probes. By cautions, be attentive. Watch what you touch. You shouldn't touch the probes while measuring voltage. The probes have sharp points so that you can make precious contact. Use the protective shields when probes not in use, so that they won't harm anyone. Observe the meter maximum limits for voltage and current. Fuse are a last resort protection feature. If you blow a fuse, you made a mistake, a very big one actually. So you must spend some time in safety so that you won't get harmed or you won't harm anyone around you. The operators of the voltmeter could be exposed to lethal voltage and current levels. Also, when probing a live circuit, careless cross contact and the resulting short circuits could route equipment, damaging levels of voltage and current to the circuit under test. So you might harm the circuit, damage components while measuring or while using digital multimeter or volt ohm meter. You must practice before going to circuits. You must practice with the components, you must practice with damaged circuits, then go to the real life circuits and real life problems. A good technique is do a dry run of probe placement with power turned off. During the dry run, the operator can see if the probe placement is correct and not short circuiting to damaging voltage and currents. Practice probe placement, and once confident, turn on the power source to make the measurement. Another good technique is to start all measurement at the highest scaling level and then adjust the scale downward to the appropriate level. There are usually automatic protection features in volt ohm meters, but it is best not to consistently depend on them doing their intended jobs. That's it for measuring voltage and for safety in measuring voltage. I know that this lesson was really long, but I'm sure that you learned a lot of things in one lecture, and we kept it connected since these all experiments are related to each other. Thanks for watching. See you next in measuring current. Hello and welcome to this new lesson in which I will teach you how to measure volt. So in order to measure voltage, you need to know few things. First, there are two types, the AC and the DC type, as we explained earlier. This watch will measure AC voltage between 2 and 750, as you can see, volt plus the AC sign here. And here it can measure from 200 millivolt up to 1000 millivolt in DC. As you can see, we have a V plus a dash means DC. So first you need to make sure that you are this digital multimeter is turned off. I want to measure DC voltage for this battery. Same for AC if I want to measure AC. For DC, as you can see, I have to go to this range, and I know that this battery is around 9 volts, so I will go with 20 volts. As you can see here, we have it set on the 20 volts, and in the COM I have to connect the two probes between COM and volt probe. So the black to the common, the red to the volt. Turn on the watch, and as you can see here, we have a positive and a negative. The red will go to the positive and the black will go to the negative. As you can see in this LCD display, we have like 9 volts, and this is the same thing that's written 9 volts DC, and this battery is also 9 volt DC. Same goes for AC. If you want to transfer to AC, if you want to test the AC voltage on your plug or in your house, you need to go to 750 here, and using the same two probes, polarity doesn't matter here. You can apply the black to the right and the red to the left, or vice versa. Then turn on the display and it will give you the AC reading here. Same concept applied for both. As you can see, it's very easy to measure voltage using this watch, but you have to make sure not to move from AC to DC while the power is on. You need to turn off, then move to DC. If you moved from AC to DC while the power is on, you might damage your digital multimeter, so you need to take care of this. So take good care and good big precautions not to do this. Stay safe. Try not to touch the probes when measuring voltage, so you need to touch the probes from this place, not from this place, because you might harm yourself. That's it for the measuring voltage lesson. Thanks for watching. Have a nice day. If you have any question, please ask in the Q&A board. I'm here to help you. Happy learning. Hello. Today we will talk about measuring current. What is current? Current is the flow of electrons through a conductor. The water analogy is that current is like the water flowing through a hose. Current is measured in amperes, and show from this illustration 1 ampere is a large number of electrons flowing past a spot in the conductor in 1 second. As you can see in this illustration, 1 ampere equals that number of electrons. I won't read it in 1 second. Current in normal electronics can be in the range of hundreds of amps to millions of an amp, micros to billionth of an amps, nanos. You will generally work with tens of amps down to micros of amps in the typical electronic devices. You won't deal with higher value than 10 amps since they require a special device for measuring them, and they are mainly used in factories, not in everyday electronics or in circuits or common circuits. So now let's look at current measurement. There is greatest potential for meter damage when measuring current than any other function. Just as in voltage, there is two kinds of current associated with the voltage, AC and DC. This meter will only measure DC. More expensive meter will measure both currents. To measure current, the volt ohm meter must be inserted into the circuit so that the current flows through the meter. There is no way that you place the positive and negative probes and say, yay, I just measured current. This won't work like voltage. You must place it in the circuit, not on the circuit. So we must again mention safety during these measurements, and we must spend some time to amplify your knowledge in how to use the volt ohm meter to measure currents the right way. And we mention that the current must flow through the meter as opposed to measuring voltage when it was only necessary to sample the voltage surrounding the source. Generally, to have the current flow through the volt ohm meter, an existing circuit must be broken and soldered, and the meter probes connected to either side of the break. The volt ohm meter then becomes part of the path through which the current must flow. There are two current ranges, high up to 10 amps and low 200 milliamps or 0.2 amps and below. Internal fuses provide some meter protection for over current situation. Because there is such a wide range of current scales, there are two physical probes jacks for the two ranges. This allows for better protection, a hard fuse to handle up to 10 amps of current, and a more fragile fuse to protect the sensitive circuits needed to measure small currents. Now we will see these two ranges in the meter, but we must read that caution. There must be some resistance in the circuit or the current flow through the circuit will be the maximum the source will produce, and this current level could damage the volt ohm meter. So you must make sure that there is some resistance. You must not connect the volt ohm meter to measure current directly and place it inside the circuit. In other words, do not connect the volt ohm meter probes directly across the battery poles in the current measurement function. This is useless and it will damage your volt ohm meter. So with no resistance in the circuit, the voltage source will provide the full current available to the circuit. There is essential no resistance in the volt ohm meter probe lines. Therefore, if the probes are connected directly across the battery poles, the full current in the battery will flow through the volt ohm meter and probably blows the fuse. So we must make sure that there is some kind of resistance in that circuit. If there isn't, you must place a resistance inside that circuit. Hello, now let's look at measuring current in practical. We will be using some concepts during the current measurement exercise that will be covered in more details later. So please be patient. It will all come together in the end. In the following exercise, you will use various resistors to limit the current flow in a sample circuit. This is the breadboard or the protoboard. This is simply a board that you use to test electronic circuits. You can place your elements here and connect power. Then you can see how the circuit function before building a more permanent prototype. Proto stands for prototyping. You need to understand the difference between the interconnected holes here. As you can see, each 5 holes here are connected together horizontally, not vertically. And the same is here. These 5 are connected together. So you can consider them as one pin. The same goes here and here. While these two, blue and red, are called power rails. So from here to this pin, this is the negative power rail, and from here to here, this is the positive power rail. So if we place, let's say 9 volt and ground, this is the ground wire and this is the 9 volt wire. If we connect them here, then all of these pins will get 9 volt. You can connect a LED to these pins, and you can connect a wire and take power from these pins, while the other pins here in that vertical line are connected to ground. So this is for connected other circuit components here and here to power and ground, and it's a really useful board. As you can see, again, the vertical rows in the center that have red and blue lines next to them are connected together. The holes in the red row are connected together. The holes in the blue row are connected together. The board, as shown, are configured to have these rows as power sources, red for positive and blue for ground or negative. There are 4 black there are 4 banks of horizontal rows. As you can see here, this is one bank, second bank, third and fourth bank. They are connected together. The horizontal rows are where the components will be interconnected, and the vertical center row will be connected to the circuit power to provide the other circuit element with power. Now let's look at measuring current basic circuit. As you can see here, this is a resistor that we will use to limit current so we won't damage our digital multimeter, and this is a battery, a 9 volt battery in that case, and this is our volt ohm meter that is connected through the circuit. As you can see here, this is the positive terminal. It's not connected directly to the resistor. We cut the circuit and place the volt ohm meter right in the middle so that the current will pass through the volt ohm meter. Now let's look at this circuit in practice. First, current measurement. Set up the circuit using 100 ohm resistor, brown, black, brown. You need to have 100 ohm resistor like this one, as you can see. Now connect a wire to the positive power source and connect another wire to the tab end of the resistor. As you can see, this is the positive power source and this is the negative power source. We must connect the first resistor wire to the positive, and we must connect the other wire to the other terminal of the resistor to a wire, then to the black terminal of the volt ohm meter. We need to set the volt ohm meter current scale to 200 milliamp, as you can see here, 200 milliamp, and we need to place the red probe in the right place here in the milliamp connector, not in the 10 amp connector. Without connecting the battery, practice touching the volt ohm meter probes to the exposed wire ends. You need to take some time to understand this example before going further. Now let's connect our battery and measure the current with the volt ohm meter set to the 200 milliamp current scale. Touch the black lead to the wire hooked to the high side of the resistor. Then touch the red lead to the lead coming from the positive side of the battery. Note the volt ohm reader. It will give you 89.2, and this is in milliamps, so the current flowing through that resistor is 89.2. Now you need to understand that we got the reading in milliamps, so if we want it in amps, it will be 0.0892 amps. You must multiply that number by or divide it by 1000 to get that amp reading. Now if we look here, as you can see, if we reverse the volt ohm meter leads, we can note that the reading became negative 88.0. This is obvious, since we reversed the two probes, we will get a negative reading. Now let's return to the volt ohm reads, return volt ohm probes to their original position. The red is connected to the battery. Change the volt ohm current ranges down and know the display reading. What is the best range for measuring the current from a 9 volt source through a 100 ohm resistor? You will notice that when you reach the 20 milliamp range, it will give you 1, and we did explain what 1 mean. It means out of range, and you mischoose the right range, while in 200 milliamp range it gave 89.2. Now let's look and wire the circuit with a 1 kilo ohm resistor, brown, black, red. This is that resistor, and measure current with 200 milliamp range. Let's see the results. What is the best range to measure the current through a 1 kilo resistor? As you can see, in 200 milliamp range, it gave us a 0 in the left, which means that we can get a more precious reading. So if we switch it to 20 milliamp, it will give us 9.4 milliamp, and if we switch to 2000 microamp, it will give us out of range. So this is the best, let's say the best range for measuring. You must test that for sure to get a clue how much current will pass and what is the best highest resolution scale. Now as you can see here, let's wire that circuit with a 10 kilo ohm resistor, brown, black, orange. These are the three colors. Let's measure the current with 2000 micro amp range. As you can see, it gave us 955 micro amp. These are different lab results. If we did another measurement, as you can see, the best range for the 10 kilo ohm resistor is the 2000 microamp, since if we choose the 200 microamp, it will give us out of range. Now another example. Let's say that this is our last example. In this exercise, using 100 kilo ohm resistor, let's start at 200 milliamp scale and read the current using each of the 4 ranges and record the result. This will be a good opportunity to again go over converting currents from amps to milliamps to microamps, and also illustrate how to determine the best range for the current being measured. As you can see, in case of 100 kilo ohm resistor, brown, black, yellow, if we started with a 2000 milliamp, it will give us 0.09. and going further it will give us a higher resolution depending on the range. That's it for the practical part for measuring current. Next we will be measuring resistance. Thanks for watching. This is Educational Engineering Team.
Hello and welcome to this new lesson in which I will teach you how to measure current. Measuring current is a little bit harder than measuring voltage because there is two ranges, the milliampere and the ampere range. So you don't want to confuse these two because this might damage your digital multimeter. So when you are measuring, if you are measuring small amp, use this one. If you are not sure, use this one because it can measure up to 10 amp. But if you measure higher than 10 amp, you shouldn't use this one. You should buy a watch that has such specifications. Now, in order to measure current, you need to move the dial here. As you can see, we have from 20 milliamp to 10 amp AC and from 20 milliamp to 10 amp DC. So let's start by stating how to measure current. In order to measure current in a circuit, you need to do a short. So you need to cut the circuit. Let's say that we have a 9-volt battery, the positive terminal, and we have a LED, a resistor, and a LED, and a ground. This LED will turn on. If we want to measure how much current is withdrawn in this circuit, we need to break this circuit. So now it will become like this. And this. These are the two probes of the digital multimeter. We must add them in series with the circuit so that we can measure the current. Now, the same thing apply to, as you can see, this is a DC volt. The same thing apply for AC. If you want to measure a current that goes through, let's say, a 200 to 20 volt AC plug. Let's say that this is the AC plug. You need to go to the digital multimeter. Then let's say that this is a light bulb. This is the line and this is the neutral. The neutral will be connected directly while the line must go through the digital multimeter using these two probes in order to measure this amp that the lamp consumes. I will show you how to do it for the DC circuit, and the same thing applies for the AC circuit. You need to cut the circuit, cut the wire, and let it pass through the digital multimeter. Then you can simply see the results on the LCD display of the watch. Now let's do this in action. I want to measure DC volt, so I must move while the digital multimeter is turned off. Let's move to the DC range. Okay, I will measure small amp, so I will go to the DC 200 milliamp. Now I will place the probes, the COM on the COM, and this one on the milliamp because I know I will be measuring on the milliamp range. Let's turn on the display, and I will take the measurement for a very simple circuit. I have it here. As you can see, we have a LED and a resistor, as I drawed earlier. In order for this to turn on, you must connect it like this. The positive terminal to the resistor and the negative terminal of the LED to the ground, and as you can see, it's on. I need to cut this circuit, so I will do the same. I will connect the negative terminal to this, but the positive terminal I will connect it through this device or through the probes of this digital multimeter. So let me just hook it up here. As you can see, now I have this probe and this probe. I will connect the negative to the battery and connect the other probe to the digital multimeter.
Hello, today we will learn about measuring resistance. When the volt ohm meter is used to measure resistance, what actually is measured is a small voltage and current applied to the component. There are 5 ranges. An out of resistance reading will indicate a single one digit. Remember, K means multiple the reading by 1000. Operating voltage should be removed from the component under test, or you could damage the volt ohm meter at worst, or the reading could be false at best. When measuring resistance, there is a small voltage supplied by the meter to energize the component. The red probe lead would have the positive voltage. The volt ohm then measures the voltage and current flowing through the component, and the resistance is calculated using Ohm's law, which will be covered later. You can go through the 5 ranges. 200 will read up to 200 ohms, 2000 will read up to 2000 ohm, 20k will read up to 20,000 ohm, 200k will read up to 200,000 ohm, while 2000k will read up to 2 million ohm or 2 mega ohm. If their power is removed from the circuit, there is little danger that the volt ohm could be damaged. So you need to remove the power before starting the test. Now let's look at an example. Measuring resistance. Disconnect the battery from the board. Remember to measure resistance. The circuit should be unpowered. Put the 100 ohm resistor in place. No additional wires are required. Select the 200 range and touch the probe leads to either side of the resistor. It will read 98.0. Now, if we look here, let's rephrase the probe leads and observe the reading. As you can see, there is no difference. It's the same reading, 98.0. So this means that the resistor doesn't have a polarity, and you can measure at any of these sides. Now let's look another example where we can discuss the resolution. Using the 100 ohm resistor, let's measure the resistance using each of the other ranges. This is the 2000, as you can see, 0, 89, and in 20k, as you can see, 0.10, the 200k, 0.1, the 2000k, 0.00. So it's like out of range, and we can't possibly measure that resistor, which is 100 ohm, using the 2 mega ohm scale. This will be seriously wrong, and we won't get a value. Note that the resolution of the reading decreases as the maximum ohm reading increases, down to the point where it is difficult to get a good resistance reading, which is in this example. Now, if we look at another example, as you can see here, using the 1 kilo ohm resistor and the 200 range, this is what we get. We used 1 kilo ohm, which is 1000 ohm. It's a way much larger than 200 ohm range, so it displayed 1, which means that there is a reading that is out of range. We must find the appropriate range to measuring the 1 kilo ohm. So if we use the 2000 ohm reading, it will give us 984 ohm, as you can see here, which is the best resolution for measuring the 1 kilo ohm. So you must choose the resolution wisely, otherwise you will get error, or you won't get an accurate result, and this will let's say that this will damage your calculations, because you mischoose the right resolution. So you need to try different resolutions to get the best value with as minimum as possible zeros in the left side, and in that case the 2000 did the trick for us. Now use the 10 kilo ohm and the 100 kilo ohm resistor. First, determine the appropriate range to use for each resistor. Second, make the resistance measurement. Third, using higher ranges, predict the reading and confirm your prediction by taking the measurement. This is a good practice that you should do, and these are a really simple, let's say a really simple steps that you can apply. Now, just for fun, use the volt ohm meter to measure the resistance offered your different body parts. The voltage and current used by the volt ohm meter is not dangerous, so you can measure the resistance through your body. Discuss your observation and how your measurement techniques could influence the readings you get from the volt ohm meter. And I think that this is a really fun practice. Probes across individual finger will read around 1.8 mega ohm. Probes held between thumbs and finger, one in each hand, will measure 1.4 mega ohm. Probes from the skin on the ankle and skin on the hand will get you a scale of reading. Dry skin versus moist skin. Dry 1 mega ohm, moist 96 kilo ohm. Lightly touching hit probes compared to a firmer grasp on the probes. Light is 1 mega ohm, while firm is 300 kilo ohm. The point here is that body contact with the probes during measurement can influence the ohm meter reading and should be avoided, particularly when measuring high values of resistance. You can bring this up again and try it yourself at home. You will know that once you touch the two probes, it will display a resistance, so you need to avoid direct contact with the resistance when measuring it, since this will damage your reading or give you a false reading. So please take care of this very important note when using the volt ohm meter or the digital multimeter to measure resistance. Thanks for watching. This is Educational Engineering Team.
Hello and welcome to this new lesson in which I will explain to you how to measure resistance. Measuring resistance is a very easy job. You just need to go here to the resistance mark, and we have from 200 to 200 mega ohm resistance. You can choose any of these, but if you don't know, you can start big, then move down to the low resistance if you don't know the resistance that you are measuring, and if you don't have a clue about the measuring range. So first thing is going here and choosing the connectors. The black will be in the common and the red will be in the volt ohm hertz diode measuring. And as I mentioned earlier, you just need to turn it on, then bring these two wires, and let's bring the resistor. This is the resistor. Place your hand on one end and the other end leave it free, and as you can see, it's measuring a number with 0.0 etc., which means that we have a smaller resistance. Let's move it to 20 kilo ohm. Now if we measured, as you can see, we have 10 kilo ohm resistor, 9.9 kilo ohm resistor, which is basically a 10 kilo ohm resistor. Now the other way to measure a resistance value is by downloading any of the resistance color coding apps on your mobile phone and use these colors, as you can see, brown, black, orange and gold, to find the resistance value. Resistance might come in many shapes. This is a typical, normal, commonly used resistor, while this one that you are seeing here is called
heat resistor. It can withstand up to 5 watts, and its value is written R4 R7, so 4.7 kilo ohm resistor, and in this case 4.7 ohm. As you can see, the R means the ohm, but when R is placed between two numbers, it means that this is replaced with a dot. Now let's try to measure this resistance. Hopefully it's working. Now, as you can see, it has a very low value. We have the result 0.01, so we need to move down to the 200 ohm measuring range. As you can see, now we have the right measuring, which is 5 ohm. As I mentioned earlier, it's 4.7 ohm. Remove the R and place dot, so 4.7 ohm. So it's basically 5 ohm, the same as measured in this digital multimeter. That's it for measuring a resistance. It's a very easy job. Even if you don't have a digital multimeter, you can measure it using the color coding on any website. Search Google for it. And as I mentioned, it comes in many shapes. These are two of the shapes. This one is heat. It can withstand heat up to 5 watts. When drawing 5 watts, it will heat up. If you touched it, you can sense some heating that's coming out of it, but it's well protected. That's it for how to measure resistance. Now let me talk about how you can check if a resistance is working or not. Now the first step would be using a digital multimeter to measure the resistance value for sure, and if you have color coding, you can check the measured value with the color coding value. If they were not the same, this means that this resistance isn't working. This is the first step. The second step, if the resistance is black or exploded, it's not working, so it's obvious. So you have to go back to the data sheet and know its value to replace it. These are the two main things that you can use to check if a resistor is working or not. Basically, the digital multimeter is the best way to check that. The second best way is by using color coding and comparing it to the digital multimeter reading. Otherwise, if it's exploded, or if it's in black, or if it's burned, or if you can smell a burn around it, it means that it's not working, so you have to replace it with another one. If the colors are there, then you can simply know using the color coding the resistance value and replace it with another one. If the colors aren't there because it's burned out, you can go back to the data sheet and replace it. Thanks for watching this lesson. If you have any question, please ask in the Q&A board.
Hello and welcome. Today we will look at circuit diagrams basics, electronic roadmaps. Basically, each diagram will contain one of these components: resistors, ground, capacitor, inductor, diode, transistor, integrated circuit, and other miscellaneous components. So you have probably tried to build a circuit using one or more than of these elements, or you searched Google for a schematic and you see a lot of the components including these, and you tried to build a circuit yourself. Today I will help you with that, and we together will build a very small but useful circuit. There are many diagram symbols used to symbolize the various electronic components, and there are minor variations in the individual symbol to represent variations with a component class. We will discuss and introduce a basic working knowledge of circuit diagrams. Circuit diagrams are roadmaps that show the pathways that current can take from the current voltage source through the individual components of the circuit to accomplish some task and return to the current voltage source to complete the circuit. The diagram symbols that will be covered are just mentioned here, and you might want to buy these components so that you can understand them in a better manner.
Let's look at this circuit. This is a remote decoder circuit, as you can see here. This is the integrated circuit or the IC. This is a relay module, power supply, which give us 9 volt. This is ground, this is transistor, this is a resistor, and as you can see it has a lot of components. This is a switch, this is a regulator, this is a diode, and this is our battery. That switch is used to turn on and off that circuit. This is a simple example of circuit diagram. In this case, the circuit decodes the signal sent by a TV remote control and turns on and off electrical relays switches in response to the keys pressed on the TV remote. This diagram is a really simple one, and these are the four, as you can see here, these are the four switches that we can use. This one, this one, this one, and this one. So depending on what we press on the remote control, one of these relays will be turned on or off. Now we will examine the simple circuit components. This symbol on the left is for fixed value of resistance, this one. The symbol on the right shows a potentiometer or a pointer that can be moved across the resistance to vary the resistance. We must point out that using various resistance is very common in volume controls, on audio equipments, dimmer light for rooms, and a lot of other examples. Generally, a symbol with a pointed arrow associated with it represents variable or changeable component. Not just the resistor, any other component with an arrow or a pointer will represent a changeable value. Now if we looked here, grounding through at first appearance is a simple topic. This is for ground. This is the symbol that we use to represent ground. It really does have some differences as represented by these two symbols for ground. A ground is a common return path to the current in a circuit to the voltage current source. By convention, the ground connection is hooked to the negative pole of the power source, so in reality the ground is the originating source of electrons. This seems to be backwards, but this is the standard convention. In the early days of automobiles, the positive side of the battery and other voltage current sources were connected to ground. This is not true today. The term grounding probably comes from the safety term related to connecting an electric device to a metal rod driven into the earth to provide a safety path for stray current to flow into the earth, and not through the operator's body. For instance, many high structures have lightning rods that are hooked to grounding rods driven into the earth so that in the event of a lightning strike, the dangerous voltage and current from the lightning strike flow harmlessly into the earth and not through humans in the place. There are two basic types of grounds as represented by the two symbols. The symbol on the left that looks like a shovel represents a ground connection to an earth ground. Represents a ground, as you can see here, it represents a ground connection to the earth ground. Commonly there is only one connection between an electrical device and an earth ground, and that connection is primarily for safety. This could be argued that the earth ground is also important for proper RF performance, but the discussion can be done in more advanced courses. The symbol on the right that looks like a rack or pitchfork, as you can see here, represents a chassis ground. A chassis ground is the metal box or foundation that the electronic device is contained in. The symbol actually represents multiple connection between components and the chassis. the chases ground is used to provide the common path for current to flow back to the power source to complete the circuit. I know that this is too much to understand, but you need to get a clue of grounding and what it really means. Now let's look at these two capacitors. This is the symbol that is used for capacitor, fixed and variable capacitor. The function and operation of capacitor will be covered in some details a little later, but you can describe the internal component of the capacitor based on the symbol. It consists mainly of two plates or two metal plates separated by a space, as you can see here. One metal plate and the other one, then there is a space between them. That is basically what a capacitor is, two conductors separated by a non-inductive space. To give just a brief description of a capacitor, we must mention that capacitors can be thought of tiny and very temporary storage batteries. Capacitors store electrical energy in electrostatic field between the plates. Anyone who has combed their hair or have taken clothing out of a dryer knows what a static electricity is. You can make a connection and test that yourself. Now if we looked at here, we can see the inductor symbol. We must point out that if there was an arrow, the inductor would be variable, as we mentioned earlier, based on the symbol. Let's try to describe the inner structure of that inductor. We can see that consists mainly of a coil of wire, or a coil of wire with something inside the coil. As a brief introduction to inductors, you need to understand that inductors store electrical energy in a magnetic field that is formed around the coil here. When current passes through it, so if we pass current through here, it will store energy in a magnetic field around that coil. Most of you are familiar with the Earth's magnetic field. One theory is that the Earth's magnetic field is formed because electrons are moving within the molten metal that makes up the Earth core. The same that happens at a very tiny scale in inductors in a circuit. When you allow current to pass through the wire, it will generate a magnetic field around it that will theoretically store energy. These three symbols are for diodes. There are number of diodes for various purposes, and as you can see, the regular diode, the Zener diode, and the light emitting diode, the one that turn on and off a light once activated. And these three diodes are used widely. Now if you look here at the transistor, as you can see, this is an NPN transistor, a PNP transistor, and a FET transistor. There is a trick to help you identify the type of bipolar transistor, which is looking to the direction of the arrow, as you can see here. If the arrow is pointing out, it is not pointing in, that is NPN transistor. And if the arrow is pointing in, it is pointing in proudly, that is PNP transistor. On the FET, the direction of the arrow identifies the material of the junction. In the illustration, the arrow is not pointing in, it's pointing out, therefore this represents an P junction FET. Now let's look at integrated circuit. As you can see, this is its symbol, this is how it looks in real life. By their very nature, integrated circuits are a collection of components that perform a specific function. It is not necessarily to know what goes on inside the IC, just how the IC interfaces with the rest of the circuit. Therefore, the symbol provides only information on which pin of the IC is connected to the surrounding components. Sometimes there is a descriptive label on a pin, for instance GND for ground and VCC for the power source. Now let's look at the final element. As you can see, these are miscellaneous elements. This is a battery, a speaker, a voltmeter, this is a fuse, and this is antenna, and this is amp meter. That's it for circuit diagrams and basic electronic components symbols. Thanks for watching. This is Educational Engineering Team. Hello and welcome. Today we'll talk about the resistor in more details. We will take a good look at resistor defined or resistance defined, resistance values, ohms, color code interpolation, power dissipation, and we will look at resistors in circuits, series, parallel, and mixed. This is the resistor symbol as we mentioned earlier. Now let's look at the first thing which is resistance defined. Resistance is the impediment to the free flow of electrons through a conductor. Friction to moving electrons. Where there is friction, there is heat generated. All materials except some resistance, even the best of conductors. Unit measured in ohms. So we measure resistance in ohms from 1 divided by 10th of ohms to millions of ohm. Now let's look at resistor types. There's the fixed value, the variable value, the composite resistive material, the wired wand, and two parameters associated with the resistors, which is resistance value in ohms, power handling capabilities in watts. So these are the two most important factors that you must take care of when mentioning a resistor or dealing with a resistor. Now if we looked here, all 100 ohm resistor, this is 100 ohm, that one, and that one. They came in different sizes, as you can see, so they can handle different amount of power. As you can see, the diameter of each one is different than the other, but they all represent the same value, which is 1000 ohm. Now let's look at this and know the different sizes between composite and wire wand resistor. As you can see here, composite types. All of these resistors could have the same resistance value even though their relative sizes vary widely. So as we mentioned in the previous example, these all have the same resistance, which is 1000 ohm, but they come in different sizes, the same as here. Now if we looked here, this is a fixed resistor. As you can see, this is how it looks, and this is another shape. While in variable resistor or potentiometer, as you can see here, that we use in most of the audio devices, this is how it looks. This is its symbol, and this is how it looks in real life. Now what really inside a resistor? As you can see here, this is a resistor opened. There is a ceramic tube, a metal end cap, as you can see here, and a coating, two connecting wires in the two terminals, and here we can see the printed values. And there is also color bands that represent the value of the resistance. If you don't have a volt ohm meter, you can know its value from the color bands. Now let's look at reading resistor color codes. First, you need to understand that each of these color has a meaning. The first one is the first band, this is the second band, and this is the multiplier, and this is the tolerance. Now we need to model how to read a resistor color code with in practice using a 1 kilo ohm resistor, brown, black, red, and tolerance band. Let's look at that 1 kilo ohm resistor. 10 resistor So gold or silver band is at right. So you need to let that band, which will be either gold or silver, in your right side or right hand side. Note the color of the two left hand color bands, which are here, the green one and the blue one. The leftmost band is the left hand value digit. The next band to the right is the second value digit. Note the color of the third band from the left, which is yellow here, as you can see. You must know its color. This is the multiplier. Multiply the two value digits by the multiplier. So we will get a 2 digits from here, then we will use this multiplier to multiply them. Let's look at let's say a more solid example, but first let us look at this color codes. If it's black and existed in the first digit, then its value will be 0, and so on for other colors until you reach the white one, which is 9. If it's in the second digit, it will have the same value, while if any of these colors existed in the third band from the left, it will be that multiplier, as you can see, 1, 10, 100, 1000. And depending on whether the right hand band is gold or silver, you can add a tolerance of 5% or 10%, or in case of no color band, it will be 20%. This is a very simple sorry. Now let's look. If we have 1 kilo ohm resistor, brown, black, red, and tolerance band, let's orient the resistor with the tolerance band to the right, the gold or silver band. If there is no band, we mentioned that it will be 20% tolerance resistor. Let's orient that resistor so the band are toward the left. Take note that the two significant digits of the resistor value are going to be represented by the two leftmost color band. Note that the leftmost band is brown, which translates to a value of 1, as you can see here. Brown means 1. And we must note that moving left to right, note that the next band is black. Black means a 0, as we can, let's say this is the black one, it's 0. This is the second digit. So now continue moving left to right. Note that the multiplier band is red, which translates to the multiple or multiplier of 100. So multiply the 10 times 100, it will equal 1000 or 1 kilo ohm. This is a really simple method to measure different values of a resistor without using a digital multimeter. Now reading resistor color codes, practical problem. If we have an orange, red, yellow, violet, orange, brown, black, brown, black, green, red, blue, gray, orange, white, orange. I need you to get the value of all of these. Take a 5 to translate these values using this table. I will upload the course material so that you can use them. You can use these slides to gain more knowledge. The results will be 3.3 kilo ohm, 47 kilo ohm, 100 ohm, 1 mega ohm, 2.2 kilo, 68 kilo, 39 kilo. Please pause that video and solve this problem before going any further. In the next lesson we will discuss power dissipation in a resistor. Thanks for watching. This is Education and Engineering team. Hello. Today we will look at power dissipation in a resistor. Resistance generates heat and the component must be able to dissipate this heat to prevent damage. Physical size, the surface area available to dissipate heat, is a good indicator of how much heat power a resistor can handle. Measured in watts, common value are a quarter, half, 1, 5, 10, etc. Now let's look at this example. Resistor in circuit series. Looking at the current path, if there is only one path, the components are in series, as you can see here. There is only one current path flowing through these resistors, so resistors are in series. And the main distinction between series and parallel circuit is how many paths the current has available to complete the course from the negative pole to the power source to the positive pole. In this diagram, all currents from the battery must pass through both resistors, therefore this circuit a series circuit. At the point you need to develop the concept of equivalent resistance. Equivalent resistance is what the total resistance would be if you substituted a single resistor, the resistor that make up the circuit. In this case, if the two resistors were to be combined and replaced with a single resistor that had the same resistance, that single resistor would be the equivalent resistor. We will get equivalent resistor and replace these two resistors with that resistor. Now if we looked here, resistors in circuit series, the equivalent resistor will be the summation of each of these resistors that are connected in series. It is easy to calculate the equivalent resistance of resistors in series. It is simple, the sum of all the resistance. The subtractive above refer the first, second, and all substitutive resistance or resistance valued are added together. For example, if R1 is 100 ohm and R2 is 200 ohm, then the equivalent resistance would be 300 ohms. Another example, if R1 is 50 ohm, R2 is 10 kilo ohm, then R3 is 500 ohm, then the equivalent resistance for these three resistors will be 10,550 ohm. Now let's take a deeper look at this circuit, R1 and R2 resistor in circuit in series. On your proto board or breadboard, set up the following circuit using the resistance value indicated on the next slide. Calculate the equivalent resistance RE and measure the resistance with your volt ohm meter. So you need to provide to connect these two values, resistors, in the breadboard and calculate the result. Then you can measure the result using your volt ohm meter and make sure that you got it right here. This is a very good example, so I suggest that you pause that video, calculate the values here, and connect these resistors to breadboard. Then write down the values using the volt ohm meter here and compare the result with the calculated one. Take 5 to do this example, then return back to this lecture. Now let's look at resistors in circuits parallel. If there is more than one way for the current to complete its path, the circuit is parallel. So the current won't return from here. It will be distributed to here and here. Then it will take two ways to return to its path. So these two are connected in parallel. Now let's look at the formula. The left hand formula is really just the same as the right hand formula, except it is for two resistors in parallel only, and the algebra has been done on the right hand formula to make it a little simpler. We must point out that by the very nature of a parallel circuit, the equivalent resistance will be less than any of the single resistors that make up the circuit. Sensitive the audience, or you need to be sensitive to this fact, so that as we go through the exercises, we need to make sure that in our results, the equivalent resistor will be less than any of the two separated resistors. This makes sense if you think about it, referring back to the waste analogy. If there is more than one hose for the water to flow through, each path has a relatively narrow hose, which is a resistance. Then what the water sees as it approaches the hose opening is not the narrow opening of just one hose, it's the sum or the total sum of all openings, which would make it appear that there is one large opening to go through. One large opening is like seeing one lower resistance path than the individual hose opening. So the thing that you need to note is this formula works for barrel resistor if there is only two resistors, and this is for more than one barrel resistor. So you need to get this right. Now let's look at a circuit example. As you can see here on your breadboard, set up the following circuit using the resistance value indicating on the next slide. Calculate the equivalent resistance RE and measure the resistance with your volt ohm meter. This is the circuit. These are the values, and please take 5 to do this example. Now let's look at this parallel challenge. Make a circuit with 3 resistors in parallel. Calculate the equivalent resistance, then measure it. If we have R1 330 ohm, R2 10 kilo ohm, R3 4.7 kilo ohm. Now let's build the circuit and see what is the equivalent resistance. Let's look at resistors in circuit mixed, which means that it has series and parallel resistors. If the path for the current in a portion of the circuit is a single path, and in another portion of the circuit has multiple routes, the circuit is a mix of series and parallel. Circuits are usually not just series or parallel. Most practices are a combination of the two. In order to analyze these mixed circuits, you need to be able to divide sections of the circuit and look at the smaller section individually. Then, once each segment is analyzed, the segments can be put back together to make the whole circuit. In this circuit, if you look at the two resistors in the lower left of the circuit here, these resistors are in series. The equivalent of these resistors is the simple sum of the two resistance values. Next, the equivalent combined resistor is connected in parallel with that right resistor, because there are two paths for electrons going into this portion of the circuit. The equivalent of these two resistors is R1 multiplied by R2 divided by R1 plus R2, which is the law that we mentioned in this slide, this one. Okay, now going back to our slide. Finally, the resistor at the top is in series with the equivalent resistor here at the bottom because the current has only one path. This is a simple manner of how we can simplify the circuit and get the equivalent resistor. Now, if we looked at this mixed circuit, okay, if we looked at this circuit, as you can see here, let's start with a relatively simple mixed circuit and build it using our breadboard. The R1 value is 330 ohm, R2 and 3 are 4.7 kilo, 2.2 kilo. Let's see how we can calculate its value. If we take these two resistors, R2 and R3, this is the law to get the equivalent value or equivalent resistance from them, since they are in parallel. Once we get that value, which will be in that case 1498, we can go further and sum these two values which are in series now and get the result, which will be 330 ohm plus 1498 ohm, and the final result will be 1928 ohm. You can calculate this yourself using a calculator or using your pen and paper. And this is a really simple example, 2 parallel and 1 series. Let's look another example. This is R1, R2, R3, R4. These are their values respectively. As you can see here, we can start by summing R2 and R3. In this, as you can see here, the equivalent resistor will be 3.2 kilo. And going further, we can RE and R4 are connected in parallel, so we can calculate their value using this law, and the result will be, as you can see here, the result will be 2230 ohm. Since the final result is 2230 ohm, after summing the equivalent value of these two resistors with the resistor in series here. This is a really simple example. I encourage you to do it at home using your pen and paper. Thanks for watching. Next we will discuss Ohm's law. This is Education Engineering team. Hello and welcome. Today we discuss Ohm's law. The mathematical relationship E equals I multiplied by R. We must at first do the math, then we will see Kirchhoff's law, a way to predict circuit behavior. It all adds up, nothing is lost. Let's first discuss Ohm's law. Okay, as you can see here in the Ohm's law, there is a mathematical relationship between the three components of electricity. That relationship is Ohm's law. E for volts, R for resistance in ohms, I for currents in amps. The mathematical relationship is E equals I multiplied by R. We can transform it so R equals E divided by I, or I equals E divided by R. In the following sequence of slides, we will be doing exercises where we will set up a circuit using resistors and voltage sources, 9-volt battery, predict current using Ohm's law, and verify our calculation by using volt-ohm meter. This is the circle of Ohm's law, EIR. E equals I multiplied by R, I equals E divided by R, and R equals E divided by I. This is a simple way to memorize the law. Now let's look at this circuit. This is the basic circuit that you will use for the following exercises. The volt-ohm meter will be moved to measure voltage, resistance, and current, as you can see here. This is here for current, and it's placed here for measuring volt or resistors. You must hook up this circuit in your breadboard so that you can keep up with the coming slides. Wire this circuit using a 100 ohm resistor. Without power applied, measure the resistance of the resistor. Connect the 9-volt battery and measure the volt across the resistor. Record your data. Now let's see, using the voltage and resistance data in Ohm's law, calculate the anticipated current. In this example, I equals E divided by R. Example data result in a current of 0.09 amps or 90 milliamps. We divided 8 by 8 volt by 98.1 ohms. These are the practical readings using the volt-ohm meter. The result is 90 milliamp. Now let's insert the volt-ohm meter into the circuit as indicated in this diagram. It must be in series so the current flow through it, as you can see here. Using the appropriate current range, measure the actual current in the circuit. How does the current compare to your predicting using Ohm's law? You need to compare the two results. There will be a slightly different value, but it won't be that different, since Ohm's law is the same as measuring in the volt ohm meter, but there is some practical let's say note that we must take into consideration, such as heat dissipation and copper loss. Now let's see the second exercise. Let's select a 1 kilo ohm resistor and calculate the illustrated circuit. Pretend for this exercise that you do not know what the voltage of the battery is. Measure the resistance with the power removed and then the current with power, and record our data. So here we don't know the voltage source. We measured the current and we measured the resistor, and using another configuration of Ohm's law, we can get E equals I multiplied by R. Using the current and resistance data in Ohm's law, let's calculate the anticipated voltage. It will equal 9.73 volt. This from the practical measurement using the volt ohm meter. Now let's connect the volt ohm meter into the circuit as indicated here. Using the appropriate voltage range, measure the actual voltage across the resistor here. How does the current compare to your prediction using Ohm's law? It will be really close. It will equal 9.7 volt in that case, and we measured here 9.7 volts, and the measured value is 9.3 volt, which are really close to each other. These are quick exercises to give you a thorough understanding of Ohm's law. Now let's look at this third exercise. In this exercise, you will use an unknown resistor. So the first one, the current wasn't known. The second one, the voltage wasn't known. Now the current, the resistor isn't known. So we need to calculate it using Ohm's law. We must first measure the current and then measure the voltage. Then using Ohm's law, R equals E divided by I will give us the current, will give us, the resistor value, which will be 3,844 ohm, or 3.82 kilo ohm. So it's really close to the real value. In the previous three exercises, we managed to use Ohm's law to get the current value, the voltage value, and the resistance value. In each case, two of the three components must be known, so that we can calculate the third component that is missing. Now let's look at Ohm's law in practice. The next series of slides or exercises will put Ohm's law to use to illustrate some principle of basic electronics. As in the previous exercises, you will build the circuit and insert the volt ohm meter into the circuit in the appropriate way to make current and voltage measurement. Throughout the exercises, record your data so that you can compare it to calculations. Now let's build this circuit. These are the resistor values, series, parallel series, and the three are connected in series together. And here we have an ammeter. Now if we look at this circuit and place, first let's measure the current flowing through the circuit using this ammeter. Then move the volt ohm meter to the other side of the circuit and measure the current here. The current should be the same as the previous measurement, since the current flowing through here is the same that going back here. Now insert the volt ohm meter at the indicated location and measure the current here. There should be no surprise that the current is the same. 4.65 milliamps. If you are doing this in your breadboard, this is the reading of the ammeter. Now measure the voltage across R1 here. Using Ohm's law, calculate the voltage drop across a 1 kilo ohm resistor at the current you measure. Here we can calculate the voltage drop. If we measure the voltage here using the current and the resistor, we can calculate the voltage. So using Ohm's law, E equals I multiplied by R. E will equal 4.65 volt. As you can see here, the value is 4.65 volt. This is the calculated value, and the voltage on the test bed using the voltmeter was 4.6. There is no 6.5, so this is a very small difference between the two circuits. Now in the next step, you will insert the volt ohm meter in the circuit at two places illustrated at 1 and 2, here and here. Record your current readings for both places. Add the currents and compare and contrast to the current measured entering the total circuit. So if we add these two currents, they must equal the main current or the main source of current. Now using the current measured through number 1 and the resistance value of R2 1 kilo ohm, calculate the voltage drop across that resistor. Likewise, do the same with the current measured through number 2 and the resistance value of R3 2.2 kilo ohm. Compare and contrast these two values or voltage values. As you can see in number 1, the value will be 3.21 volt. In number 2, the value will be 3.168 volt. The value are essentially the same, and they should be, since the voltage is the same in parallel. As you can see, the voltage here must be equal to the voltage here. Measure the voltage across the parallel resistor and record your answer. Compare and contrast the voltage measured to the voltage drop calculated. The measured value will be 3.17 on the test bed, and you can see that there is a very small difference, but they are basically the same values. Now if we looked at this example, let's insert the volt ohm meter into the circuit here. Let's compare and contrast the results. It will measure 4.6 milliamps, and if we did measure the volt here using the current you just measured and the resistance of R4, calculate what the voltage drop across R4 should be. It will equal 1.52 volt. Let's insert the volt ohm meter into the circuit as illustrated and measure the voltage. This is the practical value. Compare and contrast the measured and calculated voltage. It will equal 1.56. They are basically the same. This is one final measurement to complete this portion of the exercise. Insert the volt ohm meter indicated here. Record the three voltages measured previously across R1, R2, R3, and R4. Add these three voltages together and then compare and contrast the result with the total voltage just measured. So through R1 it was 4.6, R2 and 3 it was 3.17, while in R4 it was 1.56. The total of measured voltage was 9.33. So what you observed was the sum of the individual currents was equal to the total current flowing through the circuit. The sum of the voltage drops was equal to the total voltage across the circuit. This is Kirchhoff's law and is very useful in the study of electronic circuit. You also note noted that Ohm's law applied throughout the circuit. That's it for Ohm's law. I know that I did it really quick, but I will upload the slides so that you can grow each of these exercises one by one and apply them in your test bed. This is basically a really simple law in electronics, but you need to understand it correctly. Thanks for watching, and next we will explain capacitors. This is educational engineering team. Hello, today we will explain capacitors. Capacitor defined physical construction type, how construction affects values and power ratings. We will also talk about capacitor performance with AC and DC currents, capacitance values, numbering system, and capacitors in circuits, series, parallel, and mixed. Now let's look at this simple example of a capacitor. As you can see here, this is a battery, and this is the two capacitor plate with an insulation between them. The positive is charging the positive plate of the capacitor, while the negative is charging the negative plate of the capacitor. Now let's define the capacitor and how it works. A device that stores energy in electric field. That is the definition of the capacitor. It consists of two conductive plates separated by a non-conductive material. Electrons accumulate on one plate, forcing electrons away from the other plate, leaving a net positive charge, as you can see here. This is capacitor charging, and this is a positive and this is a negative charge in each of these two plates. Think of a capacitor as a very small temporary storage battery, since this battery is charging that capacitor and will hold its charge for a small amount of time, so it's a temporary manner. Now if we looked at here, we can see capacitors and different rating. They are rated by the amount of charge that can be held, the voltage handling capabilities, insulating material between plates. So depending on these three factors, capacitors are rated, and each of these three factors makes a very big difference between one capacitor and the other. The basic unit of capacitor is the farad. A single farad in reality can hold a very large amount of charge, and in electronic circuits, and the amount of capacitance is usually in the millionth and billionth of a farad, microfarad, picofarad, nanofarad. Capacitors are identified by the type of insulating materials between the conductive plates: air, mica, tantalum, ceramic, and polystyrene. So now if we looked at here, its ability to hold a charge. This is the positive plate and this is the negative one. The ability of the capacitor to hold a charge depends on the conductive plate surface area, that area, space between these two plates, and the material that exists between these two plates. It can be air, ceramic, and any other type of material. So the amount of surface area of the conductive plate, the larger the surface area, the more charge, and therefore the higher capacitance value. The distance between the plates, the closer the conductive plates are to each other, the stronger the electrostatic field that is developed. When the plates are close together, the attraction between the opposing poles is stronger. The closer the plates are together, the higher the capacitance. The insulating material between the plates. Certain materials are more conductive to separating the poles than others. This allows capacitors to handle higher voltage or to hold a charge longer. Certain materials are very thermally stable and will not expand or contrast as much with temperature changes therefore making the capacitive or the capacitance value more stable over wide operating temperature. Now let's look at this concept of charging a capacitor. As you can see here, let's spend some time talking about how capacitors charge. Let's use the water terminology that we used earlier to explain resistors. In this illustration, water electrons are entering the tank, which is a capacitor here, from the right, as you can see. And the rate that the water electrons enter the tank, which is a capacitor, depends on how much pressure voltage pushing on the water. So depending on how much is the pressure, more water will go up. The outlet valve on the right is closed, so water can which is electronics cannot escape. When there is no water in the tank, which is a capacitor, the reverse pressure voltage from the water electrons in the tank would be zero, and the water would rush into the tank, which is the capacitor. When the tank capacitor has all the water electrons it can hold, the reverse pressure of the electrons would equal the voltage pushing the water electrons into the tank, which is the capacitor, and the flow of water electrons would stop and remain constant. The tank, which is the capacitor, is in a charged state with the pressure voltage inside the tank capacitor equal to the pressure voltage of the water electron supply. In the beginning, the water electrons rush in at a rapid rate because there is no opposing pressure voltage built up. As the opposing pressure voltage built up, as more water electrons enter the tank, which is the capacitor, the rate of water or electrons flow slows until it virtually stops when the tank is full. So basically, this gate is closed, water will enter or electrons will enter from this gate, and it will enter fastly at the beginning since there is no voltage here. Then slowly it will decrease the speed of flowing electrons as the voltage here increases. Consider these as two tanks, one with let's say 10 volts and one empty. These will equal each other until the two tanks have 5 volts. So think of it like a tank that you are filling with water. As you can see here, this is how the capacitor look in real life. In the following activity, you will charge a capacitor by connecting a power source 9 volt battery to a capacitor. You will be using an electrolytic capacitor, a capacitor that uses a polarity sensitive insulating material between the conductive plates to increase the charge capability in a small physical package. Note the component has polarity identification plus or minus, and you need to take good care of these polarities since messing with them will result in blowing the capacitor. Now touch the two leads of the capacitor together. This short circuit the capacitor to make sure there is no residual charge left in the capacitor. Using your volt ohm, measure the volt across the leads of the capacitor. Now connect the capacitor as in this circuit, the positive to the positive, the negative to the negative terminal, wire up the circuit and charge the capacitor. Power will only have to be applied for a moment to fully charge the capacitor. Quickly remove the capacitor from the circuit and touch the volt ohm meter probes to the capacitor leads to measure the voltage. Carefully observe the voltage reading over time until the voltage is at a very low level, down to 0 volt. Now, as you can see in this illustration, this is used to discharge a capacitor. We will close the inlet and open the outlet. Then the charge will come out just like water through the outlet until it reaches 0 volt. This illustration returns to the water tank analogy to help show what happened after the capacitor is charged and allowed to discharge. The intake valve on the left is closed here, and the outlet valve on the right is opened. In the previous activity, when the volt ohm meter was connected to the capacitor, a path was opened for the electrons to flow from the capacitor. The volt ohm meter does take a little bit of current to make the readings. Initially, when the capacitor was fully charged, there was approximately 9 volt of pressure pushing the electrons down the conductor. As the voltage dropped in step with the reduced charge, the pressure pushing the electrons also decreased, causing a decrease in electron flow. How this showed up on the volt ohm meter was an initial rapid volt drop that showed down to ground. In reality, a capacitor loses its charge only after a prolonged period of time. The voltage drop is asymptotic to 0, never reaches 0. Now, the capacitor behavior in DC and AC and connecting capacitors in series and parallel will be discussed in the next lesson. Thanks for watching. This is Educational Engineering Team. The capacitor behavior in DC. When exposed to DC, the capacitor charges and holds the charge as long as the DC voltage is applied. The capacitor essentially blocks DC voltage from passing through. Once the capacitor reaches full charge, the forward voltage equals the reverse pressure. The current ceases to flow. It stops. It is essentially blocked. The capacitor behavior in AC. When AC current is applied during one half of the cycle, the capacitor accepts a charge in one direction. During the next half of the cycle, the capacitor is discharged, then recharged in the reverse direction. During the next half cycle, the pattern reverses. Essentially, it appears that AC current passes through a capacitor. And this is going to be to take a little more explaining. During the positive portion of the cycle, electrons are drawn from plate 1 and added to plate 2. The capacitor is charged with plate 2 being negative and plate 1 being positive. After the peak of the positive cycle, the capacitor begins to discharge when the cycle begins to go negative. Electrons are added to plate 1 and drawn away from plate 2. The capacitor is charged with plate 1 being negative and plate 2 being positive. If the audience looks at just one plate, the plate goes from positive to negative and back again, just as if the plate were a source of AC. Now, let's look at the capacitor behavior. A capacitor blocks the passage of DC. A capacitor passes AC. We need to summarize this. It just blocks DC once fully charged, while AC can pass through that capacitor. Let's look at capacitance value. As you can see, the unit of capacitance is the farad. A single farad is a huge amount of capacitance. Most electronic devices are capacitors that have a very tiny fraction of a farad. Common capacitance ranges are micro, nano, pico. Micro means 10 multiplied by 6 in negative 6. Nano 10 to the power of 9 minus 9. Pico 10 to the power of minus 12. And this is their sign, micro, nano, and pico. Now let's look at capacitance value. The capacitor identification depends on the capacitor type. Could be color bands, dots, or numbered. Wise to keep capacitors organized and identified to prevent a lot of work trying to identify the value, since their value can be really hard to calculate. As you can see here, this is 108 plus 2 plus or minus 2% tolerance. This is 104Z. And capacitor identification can be a little tricky and complicated. These two illustrations shows the typical numbering system. Some common example: 1 microfarad is written by 105. 0.1 microfarad is written by 104, as you can see here. 0.01 microfarad written by 103. 1000 picofarad equals 1 nanofarad equals 102. 0.047 microfarad equals 473 or 473, and 0.022 microfarad equals 223. So it's a little bit tricky to read a capacitor value, but you need to do your best, or use a data sheet, or simply use Google search. Capacitor in circuits. Two physical factors affect capacitor's value: plate spacing, plate surface area. In series, plates are far apart, making capacitance less. Charged plates far apart, as you can see here. These are two capacitors. They are treated like resistors in parallel. C1 multiplied by C2 divided by C1 plus C2. While, as you can see here, capacitors in circuits in parallel, the surface area of the plates add up to be greater and close together, as you can see here. While here they are apart, the positive and negative. This makes the capacitance more the capacitor. So the plate area is more. This means the capacitor is more. So the total will be C1 plus C2. This is a simple method. Another way to memorize this is to consider the capacitor as the reverse of a resistor. The resistor in series equals R1 plus R2, while capacitor in series are the same as resistor in parallel. C1 plus multiplied by C2 divided by C1 plus C2, as you can see here. Here the capacitors in parallel, C1 plus C2, or resistor in parallel, equal R1 multiplied by R2 divided by R1 plus R2. The surface area of the conductive plates in parallel capacitor add together. The electrons on the plates connected to the negative poles of the source spread out across both capacitor plates. The positive change absence of electrons on the plates attached to the positive pole of the source also spread out. The plates are still only separated by the same distance as if there was just a single capacitor, so there is more electrons are exposed over a greater surface but at the same distance. Therefore, the capacitance will be more, the simple sum. That's it for capacitors. Next, we will discuss inductors in more details. Thanks for watching. This is Educational Engineering Team. Hello and welcome to this new lesson in which I will explain to you how you can test a capacitor. So, as you can see, here we have a lot of capacitors. Okay, let me show them to you. They come in many shapes. The parallel shape or the circular shape, this one, is called a polarized capacitor. It has polarity, so this is the negative terminal, as you can see, the small or the short one, and we have the negative here sign, and this, the other one, is the positive terminal, so it's polarized. The same thing happens with all of these. As you can see, there is a silver line for the negative terminal, same here, silver line for the negative terminal, same here, also silver line for the negative terminal, but this one is not polarized, so you can connect the positive to any of these terminals and the negative to the other one, and you can reverse them without any problems. But in this case you can't. You must connect the negative terminal to this short leg and the positive terminal to this long leg, so that's why it's called polarized. Now, to test out a capacitor, you need to have a digital multimeter that can test capacitance. the one that we have here can measure from 2 nano up to 200 microfarad. There is a more specialized digital multimeters for capacitors that can be used to measure a wider range. Now, the ones that we have here, as you can see, you can find its value from here, 2200 microfarad, 16 volt. It can withstand negative 40 to positive 85 degree. But we can't test this using this watch because it can only measure up to 200 microfarad, and this one is 2200 microfarad. So let's find another one. As you can see here, we have this one. It's 22 microfarad, 63 volts. So we can test it out using this watch. So now let's test it out by moving to the 200 microfarad. Then we must connect, as you can see here, we have a capacitor sign between these two lines. So we need to connect the two probes between these two, not using the common between these two because the capacitor sign is between them here. So let's connect this here and the other one here. Now we have our digital multimeter up and ready for measuring the capacitance. So again, let's repeat the last few steps. First, you need to set to the 200 microfarad using this dial. You need to move these two. As you can see here, we have a capacitor sign, so we need to move these from the common to these places between the capacitor sign, the two probes. Now turn on the watch and bring these two probes. It's better to short circuit the two terminals first before measuring. Then you can simply add one of these two terminals, as you can see, and the other one is here. So it gave us, as you can see in the display, LCD display, 19.8, 19.9, and this is very close to the reading on it. It has a reading of 22 microfarad, 63 volts. It gave us like around 20 microfarad. So fair enough. This means that this capacitor works correctly without any problems. That's it for how to measure a capacitor. You need to make sure that when you buy a watch, a digital multimeter, it has the range that you are going to use or measure. Because this one, as I mentioned earlier, measures between 2 nano and 200 microfarad, and this is not a very large, let's say, range. That's it for this lesson. If you have any question, please ask in the Q&A board. Thanks for watching. This is Educational Engineering Team.
Now turning to the inductors. We will talk about inductance defined, physical construction, how construction affects values, inductor performance with AC and DC currents, as you can see here. This is the inductor symbol. Inductors are essentially coils of wire that are used to store energy temporarily in a magnetic field. Inductors, when combined with capacitors, are used in many different kinds of electronic circuits because of their property to oscillate or ring energy in one component feeds the other, back and forth in an oscillating or ringing manner at a specific frequency. This phenomena is called resonance. Additionally, paired inductors in close proximity with overlapping magnetic field allow energy to flow from one inductor to the other by inducing a current in the other inductor. This is basically how a transformer works. These concepts are beyond the scope of this basic course. However, the audience should be aware of the basic function of the conductor. Now, there are two fundamental principles of electronics. 1. Moving electrons create a magnetic field. 2. Moving or changing a magnetic field cause electrons to move. An inductor is a coil of wire through which electron moves, and energy is stored in the resulting magnetic field. Like capacitors,
inductors temporarily store energy. Unlike capacitors, inductors store energy in a magnetic field, not an electric field. When the source of electrons is removed, the magnetic field collapses immediately. As you can see, this is a conductor that has current passing through it, and this is the magnetic field. Now, the inductor are simply a coil of wire. It can be air wound, nothing in the middle of the coil, just like this one. Can be wound around a it can be wound around a permeable material that concentrates magnetic field, just like this example, or this example can be wound around a circular form toroid, like this one, and the second example is this one, while if nothing is in the middle, it's like this one. So depending on the core, it can have different properties. Inductance is measured in Henry. A Henry is a measure of the intensity of the magnetic field that is produced. Typical indicator values used in electronics are in the range of millihenry, 1 divided by 1000, and microhenry, 1 divided by 1 million. Let's look at the amount of inductance. As we know, the amount of everything is affected by a lot of values. The amount of inductance is influenced by a number of factors: number of coil turns, number of these turns, diameter of coil, the diameter of this coil, this is the diameter from here to here, spacing between turns, the space between each one turn and the other, size of the wire used, the size, the thickness, and the type of material inside the coil. So if it's air, if it's metal core, it will affect the amount of inductance. As you can see here, this is the air core, this is the iron core, this is the soft iron core, this is a large diameter, this is a small diameter, this is close spacing between turns inductor, and this is wide spacing between cores inductor. All of these affects the inductance of an inductor. Now, inductor performance with DC currents. When DC current is applied to an inductor, the wire in the inductor momentarily appears as a short circuit and a maximum current flows. As the magnetic field builds charges, there is a tendency for the current flow to slow down due to an opposition cause in the charging magnetic field or the changing magnetic field. Finally, the magnetic field is at its maximum and the current flows to maintain the field. As soon as the current source is removed, the magnetic field begins to collapse and creates a rush of current in the other direction, sometimes at very high voltage. While inductor's performance with AC currents, when AC current is applied to an inductor during the first half of the cycle, the magnetic field builds as if it were a DC voltage. During the second or the next half of the cycle, the current is reversed and the magnetic field first has to decrease the reverse polarity in step with the changing current. Depending on the value of the inductance, these forces can work against each other, making for a less than simple situation. Now, because the magnetic field surrounding an inductor can cut across another inductor in close proximity, the changing magnetic field in one can cause current to flow in the other, which is the basic of transformers. As you can see in this example, this is a simple transformer. Pairs of conductors in close proximity is another important use of inductors in electronics. The household transformer that converts 120 volt AC wall current into current that will run a 12 volt DC radio probably use a transformer and other circuits to do the conversion. It is important to go back to the two fundamental principles stated earlier in this unit. Moving electrons create magnetic fields, and changing magnetic fields cause electrons to move. This would be a good opportunity to walk yourself through the process while see how transformer really work. In the next lesson we will talk about diodes. Thanks for watching. This is Education Engineering Team.
Hello and welcome to this new lesson in which I will explain to you how to test out an inductor. Basically an inductor is a coil, and here we have a transformer. It has a primary coil and a secondary coil. So we can use these two coils to demonstrate the inductor measurement thing. So it's really easy. You just need to bring your digital multimeter and apply these two to the COM and the volt, ohm, diode and hertz reading. As you can see here, the red on the COM, the red in the volt, ohm, diode, hertz, and the black is on the COM. Now move this dial to the diode or the let's say sound buzzer or connectivity button, and make sure that it's working by simply testing this. As you can see, it's working. Now if you test the primary coil, it has a very high resistance, so it won't display or it won't show connectivity. It will just display the resistance value. As you can see, we have like 100 ohm resistor or resistance. Okay, 100 ohm. Now the primary resistance is usually high, so as you can see here we have 100 ohm resistor, while the secondary resistance is very small. So it's this is because it's taking like 220 volt AC in the primary coil, and it gives only 606 volt on the secondary coil. So this is a center tab. We have the black wire and we have two blues. When we connect these two, we will find half the resistance of the secondary coil, and you can see that using the connectivity test you can test this out. Okay, let me just, as you can see, this means that the secondary coil is working. Now let's test the other one. Again, there is a sound. This means that this is also connected. Now most likely when you test an inductor, if it didn't show connectivity or a resistance, a small resistance, this means that there is a cut in it or there's a problem with that inductor and you have to replace it. So there is two types of tests for the inductors. The first one is the connectivity test. The second one is the resistance test. So let's test using the resistance. We can measure the resistance. So this is a center tab, so the same resistance must appear on the black and blue and the black and this one. So the first blue wire will give us a resistance with the black wire, which is the very same resistance as between this black wire and blue wire here. So let's test the first resistance. Okay, as you can see, we have like 0.8 or 0.5 ohm resistance on the LCD. Now we must get another 0.5 between these two. Okay, let me just, okay, again 0.5, 0.4. So the total resistance between the two blue wires will be the sum of these two resistance, which is basically 1 ohm or okay, let me just fix this to the table. Okay, as you can see, 0.8, 0.7, and this is the sum of the two resistance that we just measured. This is for the secondary coil. It's a very low resistance, around 1 ohm, while the primary coil has a very high resistance. So if we brought these two, this one,
if you check the LCD, you can see that we'll have around 100 ohm. Okay, 77 ohm, which is like 77 times larger than the secondary coil resistance. So this is how to test the inductance of a coil and if it's connected or not, if it has a problem or not, by testing using the connectivity test here or using the ohm test here, because a coil is basically a wire, an inductor is basically a wire that has a resistance that you can measure. For sure there is other specialized devices for measuring inductance, and it gives you the inductance value not in ohm or connectivity, it gives you the very same inductance value, but we are using this simple digital multimeter to test out this thing, because buying an inductance digital multimeter would cost you a lot. So using this simple device, very cheap device, you can test inductance using the connectivity or the resistance test. These are the two tests you can use to measure inductance. If you have any question regarding this, you can ask in the Q&A board. I'm here to help you. Thanks for watching. This is Educational Engineering Team.
The diode. The semiconductor phenomena. Diode performance with AC and DC currents will be discussed. Diode types, basic, lead, and Zener. This is the basic symbol of diode. That line indicates that this is the cathode and this is the anode part. The diode is a device that allows current to flow in only one direction. There are specialized diodes, the light emitting diode and the Zener diode, that will be discussed later. However, the basic principle is the same here. The current will flow in one direction. If current flow is attempted in the opposite direction, the flow will be blocked. Diode find use in many electronic circuits nowadays. Now let's see the diode, the semiconductor phenomena. Electrons in a metal form a sea of electrons that are relatively free to move about. Semiconducting materials like silicon and germanium have fewer free electrons. Impurities added to semiconductor material can either add free electrons or create an absence of electrons, which is holes. So if we looked at this small schematic, this is the N-type and this is the B-type, which is holes. N-type are electrons, as you can see here. They are equivalent currents, electrons and holes. This is the cathode and this is the anode, and this in the middle is the depletion region or the junction of the diode. Consider the bar of silicon at the right. One side of the bar is doped with negative material, excess electrons, the cathode, while the other side is doped with a positive material, excess hole, the anode. In between is a no man's land called the p-n junction. This is the depletion. In the depletion region, this is the p-n junction that forms a diode. Now, if we looked here, consider now applying a negative voltage to the anode and a positive voltage to the cathode. If we did that, the diode is reverse bias, meaning no current will flow, and this region will be away much wider, which means that fewer electrons will pass or no electrons at all. This is the reverse bias of the diode. While in this manner, if we connect a negative portion for electron, consider now applying a positive voltage to the anode and a negative voltage to the cathode, the diode is forward biased, meaning current will flow since this area is minimized, and electrons applied here allow these electrons to go to that junction, and the positive value applied here allows hole to go to this side. This will make that area, that depletion area, as small as possible, which will allow current to flow. Now if we look at this circuit, set up the circuit illustrated on the proto breadboard, a resistor, diode and a battery. Ensure to note the cathode banded end of the diode. The cathode is connected to the resistor. Use a 330 ohm resistor. The resistor in the circuit is a current limiting resistor.
So we are using it to limit current so that it won't blow the diode. Now set up the circuit illustrated in the prototype. Ensure to know the cathode. The cathode is now connected to the battery negative terminal, and the anode is connected to the resistor, and examine the difference between these two circuits. Build the isolated circuit. Measure the voltage drop across the diode that is forward biased. It will equal 0.7, which is the amount of volt that is required to build a forward bias situation for the diode. This is the simplest manner to say this. Now, if AC is applied to a diode during one half of the cycle, the diode is forward biased and current flows. During the other half of the cycle, the diode is reverse biased and stops current. This is the process of rectification, allowing current to flow in only one direction. It's commonly used in changing AC into DC. As you can see here, this is the AC signal and this is the output of the diode. It only allows AC to flow. As you can see, the positive portion of the signal only flow. The negative is 0 since it's reverse biased for the diode. This is commonly used in rectification circuit for turning AC signals to DC signals. Now let's look at the light emitting diode. In normal diodes, when electrons combines with holes, heat is produced. With some material, when electrons combine with holes, photons of light are emitted. LEDs are generally used as indicators, though they have the same properties as a regular diode, but instead of dissipating heat, they are dissipating light. This is a simple circuit that can light a LED. Build the regulated circuit on the protoboard. The longer LED lead is the anode. In the diode, you will see two leads, a long one and a short one. The long is the positive end, the short is the negative. The reverse the LED and observe what happened. Now you need to reverse that LED and observe what will happen. You will note that it won't turn on. The current limiting resistor not only limits the current but also controls LED brightness. So if we place let's say a 1000 ohm resistor, the light will be dimmed. If we place a 100 ohm resistor, the light will be the LED will be brighter. Next we will look at Zener diode. Okay, this is the symbol of the Zener diode. The Zener diode is designed through appropriate doping so that it can conduct at a predetermined reverse voltage. So the difference between it and the normal diode is that it does operate in the reverse direction. The diode begins to conduct and then maintains that predetermined voltage. The over voltage and associated current must be dissipated by the diode as heat. Zener diode is constructed so that it will conduct when reversed bias above certain voltage. The excess voltage and current then is conducted to ground and the energy is dissipated as heat. A Zener acts as a simple voltage regulator. In the case, a 9-volt source, as you can see here, is passed through current limiting resistor to drop the voltage somewhat to take the pressure of the Zener. If the Zener was not in place, the amount of voltage drop across the resistor would depend on the amount of current being down from the circuit. With the Zener in place, the 4.7 volt would be maintained by the Zener acting as a path for the excess current that is not being drawn off. This excess current has to be dissipated as heat. Therefore, there are current limits on Zeners that the designer need to consider. That's it for diodes. Next, we will discuss transistors in more details. Thanks for watching. This is Educational Engineering Team. Hello and welcome to this new lesson in which I will explain to you how to measure a diode and check if it's working or not. This can be done using this digital multimeter. Just choose the diode. As you can see here, we have a diode. Move to the diode and move the red to the diode. As you can see, I already placed it in the diode measuring, and the common to the black wire, red to the diode measuring, and turn on this display. Now this is the diode. As you can see, usually this silver line is the negative pin, so I will connect it to the common, and the black end is the positive. As you can see, it's measuring 599. If I reversed it, so if I place the black on the positive end and the silver line on the positive, as you can see, it's not measuring. So this is the reverse bias, so it's not giving me a value, while in forward bias, where I place the negative on the black and the positive on the red, it will give read. If it gives reading on both ways, this means that this is not a faulty diode, or as you can see here, this one is working because it's measuring only on the forward bias. Forward means that this line, silver line, this is the negative end, so I connect to the negative common probe of this digital multimeter, and the positive is connected to the positive, so it's giving me a reading in the forward bias. While if I reverse the connection, the black to the positive and the negative to the positive probe, it will give me no readings. So in the reverse bias, it's not giving any readings. This means that this diode is working efficiently and there is no problem with it. That's it. Again, you need to know that the silver line means this is the negative or the cathode, and the other end is the anode. So anode is connected to the positive probe and cathode is connected to the negative probe, and it will give me reading. If I reversed it, this is the forward connection. If I reversed it, it will be reversed connection, so it won't give reading. If it gave reading, this means that it's not working. And to replace it, you need to take the number. As you can see here, we can see it's written 1N4007, so you must replace it with the very same one, as you can see, because different diodes are used for different voltage, so you need to make sure that you choose the right one. Again, if it's burned out or blown, you must go back to the data sheet to replace it with another one. Otherwise, you have to guess it. If you guessed, you have to take the risk, and you might explode your entire circuit if you placed a wrong diode. So try not to guess it unless you are very desperate. Thanks for watching. This is Education and Engineering team. If you have any question, please ask in the Q&A board.
The transistor. Today we will discuss transistor and how they work, an inside look. Then we will talk about basic types, NPN and PNP. Then we will see basic transistor circuits, switch and amplifier. This is the transistor symbol, as you can see here, and this is the internal structure of the transistor. It consists of collector, base, emitter, two diodes. Though you cannot make a transistor simply by putting two diodes together back to back, it is useful to look at the transistor as made up of diodes to better understand what is happening inside. Now let's see this simple transistor registration. Take a look at this representation of the inner working of a PNP transistor. Close inspection reveals that there are two diodes with their P poles connected together. This is the P pole. The PN junction is represented by the narrow black line. In an actual transistor, the P material would really be just a very narrow strip of material, not as represented in this graphic, but this is for making things easier to understand. In this circuit, a power source is applied between the base and the emitter. As you can see here, this is the base and this is the emitter. The positive volt to the base is negative to the emitter, and additional power source is applied between the collector and the base.
the negative volt to the base, the positive volt to the collector. The base emitter diode is forward bias, which, remember, cause that diode to conduct electrons, allowing the electrons to move left to right and the holes right to left. Now, as you can see, something interesting happens in this case through the transistor effect. As the electrons from the base emitter diode go across the p-n junction, the p layer is so thin and there are so few holes to accept the electrons that the electrons continue to flow right and cause the base collector diode to start conducting and allowing the current to pass through the transistor to the collector. In effect, a small forward bias on the base emitter diode causes the transistor to turn on and pass current through the emitter to collector junction. So basically you can either forward or reverse bias a transistor by controlling its base voltage. You need to forward bias one of the junction to allow it to flow. We will see this in more detail once we go next in the switch and amplifier circuits. This is the same circuit but in a reverse bias manner. This space is connected to the negative pole, as you can see here, so positive connected to negative will increase these two areas, isolating areas, so no conducting is here, while in the previous example as you can see here, positive is connected to this positive terminal, so it's forward bias and positive holes will go there and there connected with electrons, so this area will be reduced, this insulating area, and it will conduct, while in the second case the negative will attract the positive holes, which will make this area wider and will allow electrons to pass. Now if we look at the transistor, there are two basic types of transistor depending on the arrangement of the material, PNP and NPN, as you can see here. As easy phrase to help remember the appropriate symbol is to look at the arrow, PNP pointing in proudly, NPN not pointing in, N not B pointing N in, PNP pointing in proudly. So this will help you remember the arrow direction and identify the transistor depending on that arrow. The only operational difference is the source polarity. NPN not pointing in, PNP pointing in proudly. Now if we looked here, the transistor as switch, during the next two activities you will build a transistor switch and a transistor amplifier. The pin out of the 2N3904 transistor is indicated here, as you can see. You must purchase it or you can simulate it using Protas. The transistors as a switch, build the circuit as you can see, this circuit. Use hookup wire to serve as switches to connect the current to the transistor base here. What happens when you first apply power when the base is left floating, not connected? Now as you can see here, we have a LED, 300 ohm resistor, 330 ohm resistor in the collector to limit the current flowing through the LED. Remember, when the transistor begins to conduct, the path through the transistor is very low resistance. Without the current limiting resistor, too much current will damage the component. Additionally, the 1000 ohm resistor in the base circuit also limits current. In this case, when the base emitter diode conducts, there is a low resistance path. Without current limiting, the transistor can be damaged. When the circuit is completed, nothing should happen because the base emitter diode of the transistor is not biased, so the transistor does not conduct. Now, when the base is connected to the 9 volt, The base emitter diode is forward biased and conduct. This in turn turns on the transistor and current flows through the lid to turn it on. You should note that the lid goes off when the base voltage is removed. Now if we look at and replace the hookup wire connection with a connection to a 1.5 volt battery as shown, what happens when plus 1.5 volt is applied to the base? What happens when the battery is reversed and 1.5 volt is applied to the base? Examine this on your protoboard or test bench, then get back to this video to see the result. When the voltage is positive on the base, the transistor conducts and the lid is lit. They are controlling a much larger voltage with a small voltage. This is the base. This is the goal from this circuit, to show you that we can control, using a transistor, we can control a high volting output using a small volt input in the transistor base. This will become more important in the following circuit when a transistor amplifier is explored. But for now, you need to understand that we can use small volt on the base to control high voltage output. Okay, now let's see this circuit. The voltage across the variable resistor is the battery voltage. The wiper of the variable resistor taps off the resistor at different places depending on how the screw control on the variable resistor set. The variable resistor become a voltage divider so that the voltage on the base can range from ground, no voltage, to 9 volt and all volt in between. When the circuit is wired, you can adjust the range until the lid is fully lit. Using the volt ohm meter, measure the voltage of the base of the transistor and record the value. On the test bed, the voltage was 0.78 volt. So this is the amount of volt that is required so that the lid can fully lit. Next, you can decrease or decrease the voltage by adjusting the variable resistor until the lid is just barely visible, and again measure the base voltage. On the test bed, the voltage was 0.68 volt. Finally, move the variable resistor until the lid is fully off and record the voltage. On the test bed, the voltage was 0.63 volt. As you can see, depending on different value of the base voltage, we can examine different behavior of the lid. Hello and welcome to this new lesson in which I'll explain to you how you can easily test a transistor. So first, let me explain this in theory. Basically, a transistor has 3 terminals: a base, a collector, and emitter. And we have 2 types of transistors, BNB and NBN. You need to concentrate on the letter in the middle here, the N and the B. Okay, let me just focus on this area. Now, first thing you need to know before testing a transistor, to know its terminal and to know if it's working or not, is to identify the base. So the base can easily be identified if you use the digital multimeter on the diode reading, because basically a transistor consists of 2 diodes, and the 2 terminals that won't give a reading both ways are the collector and emitter. This means that the first thing that we are able to identify is the base. So if we found 2 terminals that give no readings, you can easily know that these terminals are the collector and emitter. The base is that terminal that you used and that these 2 didn't give a reading with. So we identified the base. Now, after identification of the base, you need to know if this is a BNB or NBN. This can be done by simply testing the base using the positive terminal of the digital multimeter and try to get a measurement out of these two. If the base gave a reading when it's connected to the positive terminal, this means that the transistor is NPN because it's positive in the middle. While if we connected the negative terminal of the digital multimeter and it gave a reading with these two terminals, this means that this transistor is PNP. The last step here is to identify the collector and emitter. The emitter is the terminal that gives a higher reading than the collector when connected to the base. So if we connected these two, the collector, the base and the emitter, it should give us a higher reading than when we connect these two terminals. Now I will do this in practice so you don't have to worry about anything. If you didn't understand my explanation now, it will become clear when we do this in practice. But the main thing, let's summarize, is first identify the base by finding the two terminals that gives no readings together both ways. So you put the positive terminal of the digital multimeter here and the negative here, it will give no reading. If you reverse these two terminals, the positive here and the negative here, it will give no reading. So basically you identify the base, which is the third terminal. The next step will be identifying if it's PNP or NPN by knowing the base voltage is positive or negative. Third step will be identifying the collector and emitter. The one that will measure or will give a high reading with the base will be the emitter, the other one is the collector. In the next lesson I will show you this in practice, so stay tuned. Thanks for watching this lesson. If you have any question, please ask in the Q&A board. Happy learning. Hello and welcome to this new lesson in which I will show you how to test a transistor and how to identify its terminals. This is a transistor, as you can see here. It has 3 terminals and we will test it out and see if it's working or not and identify its terminals. As I mentioned earlier, this is basically a diode, so you have to choose the diode reading from here on the watch and or on the digital multimeter, and then you can move these terminals, the black one in the common and the red one on the one that has sorry, a diode icon. So place it here, turn it on. Now we said that the first step would be to identify the two terminals that won't give a reading when they are together. So if we came here, as you can see, you must concentrate on this. So the two terminals that won't give any reading both ways will be the collector and emitter. So let me test these first two. So no reading. Let me reverse it, the black and okay. Now as you can see, we have a reading on the LCD display of the digital multimeter, so these are not the two collector and emitter. Let's move on to the next two. So this one and this one, we have no reading, and again this one and this one, we have no reading on the LCD display. One means no reading, so this one and this one are the collector and emitter. So this one is the base. This is the first step. So let's draw it here. Okay, let me just focus on this area. So we have the base identified. Now we need to know if this base is or if this transistor is PNP or NPN. What we need to do is simply first knowing that the base will give a measurement with both collector and emitter. So if we connected the positive terminal to the base and if it gave reading with these two terminals, it means that positive means NPN, so it will be an NPN transistor. If it didn't give a reading, we have to reverse it. We have to connect the negative pin here to the base, and if it gave a reading, this means that the base is negative, or N, which means that this is a PNP transistor. So let's start. This is the positive terminal connected to the base, and let's connect it to this terminal. It gave a reading on the LCD, as you can see here. If you connect it to the other pin, it also gave a reading. So this is the base. It's connected to the red probe. This means that it's NPN transistor. So NPN transistor, this is the type of transistor. Now to the final step, which is identifying the collector and emitter between these two pins. Now, as I mentioned earlier, the one that will give higher measurement when connected to the base will be the emitter. So let's connect the positive terminal to the base. Let's connect this to this pin. It gave us 675. Let's connect to this pin, 689. So this one has a higher reading, which is this terminal. As I mentioned earlier, the one that will give higher reading with the base will be the emitter. So now we have this as the emitter, and the last one is the collector. So this is our transistor. It's fully functional, it's working, and we did found out that it's, so this is our transistor. It's NPN type. And to summarize things, first identify the base by testing collector and emitter. As I mentioned earlier, we can identify the base by testing the two terminals that gives no reading when connected with the two probes of the digital multimeter. As we did earlier, these were the two terminals that gave no reading. So the third pin will be the base. Now, after identifying the base, we need to identify type. Identify type, NPN or PNP. Depending on the letter in the middle, if we connected the red probe to the base and it gave reading with the C and E, so it's NPN. If we connected the negative or the black probe to the base and it gave reading with the collector and emitter, it's PNP. The one that we have here gave reading with when we connected the red probe to the base and the black probe to the collector and emitter, it gave reading, so it's NPN type. The third and final step would be test base to emitter, base to collector. This should give higher reading on digital multimeter. So the one with the higher reading is basically the emitter, and this is what we did here. It's the emitter. This terminal, it gave us like 689, and this gave us 675. So it's a very slight or very small difference, but it's there. So this one is the emitter and this one is the collector, as we mentioned here, base, collector, emitter. So that's it. This is how to test out a transistor using a digital multimeter. If you have any question, please ask in the Q&A board. I'm here to help you. This is Educational Engineering Team. Thanks for watching.
Hello and welcome to this new webinar, in which we are going to talk to every one of you about how to start successful career in embedded system. What are the things that you can do to get started in the world of embedded system and to start a career there? This is Ashraf Al-Madhoun. I'm the CEO and founder of Educational Engineering Team, and I'm here to welcome everyone with us today. Now, let's get started with what we have here, which is a quick introduction. I'm Ashraf Saeed Al-Madhoun. I'm a CEO, as I already mentioned, in Education Engineering Team, and I'm welcoming everyone here with us. With over 12 years of experience, 11 to 12, I have in the embedded system industry since 2012. And I've been in this industry for so long that I created more than 200 online courses. And right now, we are on the edge of 1.5 million students joining all of our online courses and getting certified in different fields in embedded system. And I'm here today to tell you, let's say, the exact step-by-step blueprint that you can follow to become an embedded system developer. You can get started with zero experience after you follow the steps that I will mention in this webinar. So I will share with you the strategies that have directly earned me and my students multiple six figures income with just learning embedded system programming. Now, let's get started. Now, there is a lot of misconception in the embedded system field and in the programming industry, especially when we are talking about embedded system. Many people believe that you need advanced degree or years of experience to start a career in embedded system. But this is one of the biggest mistakes. In fact, with the right training and guidance, you can start building your career in embedded systems today. And let's see how. The myth that you need a university degree to start a career in embedded system is all wrong, especially these days. Now, the truth that with the right training and guidance, you can start building embedded system today and you can start a career in the industry. Now, let's take a quick introduction to embedded system in case you don't know what are embedded system or in case you joined our email list or our embedded system courses without having a knowledge of what is actually an embedded system. Embedded systems are specialized computing systems that perform dedicated functions with larger mechanical or electrical systems. They are backbone of modern technology from smartphone to automotive, even the air condition and the refrigerator or any device that you can think of. Embedded system is there in the programming aspect of this device. Now, what is the importance of embedded systems? Understanding embedded system is crucial because they are integral to numerous industries, including automotive, healthcare, consumer electronics, and industrial automation. Mastering embedded system open up vast career opportunities, and this is why we are going through this webinar today with every one of you. Now, the traditional approach for learning embedded system or for embedded system in general, most people believe they need to attend a 4 or 5 year university program to learn embedded systems, leading to significant time and financial investment, which could not lead to a successful career. While why traditional programs don't work? Traditional university programs often focus on theoretical knowledge and may not provide the practical skills required by the industry. This can lead or leave graduates unprepared for real-world applications, which will lead to a shock. You are having a university degree, but you don't know how to tackle practical aspects of the embedded systems, or you don't have enough knowledge in embedded C, and you only know basic C programming, which will lead to a disaster once you graduate and you go to the work or you go to a factory or to an embedded system company and you see how there is a huge gap between what you learned in the university theoretically and what you have to apply in the actual life. Now, the better approach is to enroll in online courses that are dedicated to show you the step-by-step approach or blueprint to become an embedded system developer and to start a career in that business. Basically, what we are talking about here is that you can get started easily in no time if you know exactly what to do and what are the areas that or the skills that you need to grasp to get started as an embedded system developer. So you need to teach by making hands-on projects, by following practical steps, not just theoretical steps. You need to ensure that you can gain the skills needed to succeed in the embedded system industry. So the traditional way is to focus on theoretical knowledge, and most people fail in that and they don't find a job. They don't even find a freelancing job online in the embedded system, even though there is a huge opportunities there. And our approach is to combine theoretical knowledge with practical hands-on project so that you can learn everything from scratch, starting with basics of C, then embedded C, and moving forward to circuit design, 3D design, and programming microcontrollers. So the proof of success for us. Now, there is a proof that you can see on different online teaching platforms like our number of students. Now, the official number of students that we have, the unique number of students, is 500,000 students. But I already mentioned that we have around 1.5 million students. And this is true because at least one of every one students have joined 3 courses. And when we talk about 500,000 students, we are talking about counting only 1 course per student. Now, if we counted the number of courses enrollments, we have around 1.5 million. So at least every student we have has joined at least 3 courses. So multiplying 500,000 by 3 will result in 1.5 million students. And we have the proofs to show these results in different platforms. There is also now our academy has helped over 500,000 students, as I already mentioned. Our students have gone on to work in leading tech companies and have successfully started their own businesses in embedded systems. We know students who have now launched businesses where they can turn ideas to products and they are working as freelancers or as dedicated companies. Now, the career outcome for us is that leading companies and successful businesses started with only being a student with no knowledge to becoming an embedded system developer or having a career in embedded system. So we have a lot of proofs that you will see along the way. Now, quick tip. Start with a simple project when you are getting started in embedded systems, such as programming an Arduino, which is a geek's board, to control an LED. This hands-on experience will build your confidence and foundational skills. Don't start with complex projects. This is how we teach our students. We always start with simple projects and we write the codes line by line. So the step one would be choosing a simple project like turning on a LED or controlling an LED using a switch. Then you have to program your Arduino. And lastly, you can easily control that LED. Now, this will build momentum that would help you moving on to more intermediate and advanced projects. So always start small, then go big. Now, the key skills for embedded systems. Let's talk about that. Embedded systems are everywhere, as we already mentioned, from smartphones to cars to medical devices and industrial robots. To excel in this field, you need a strong foundation of essential skills. And these skills you cannot learn on your own, or you cannot spend a lot of time trying to find YouTube videos to learn these skills because you have to learn using a learning path that is dedicated to you. Now, why these skills matter? Understanding embedded systems requires more than just theoretical knowledge. You need to be able to design, develop, and troubleshoot these systems effectively. Without these skills, it's changing and challenging to create reliable and efficient systems. Now we have the hardware design, programming, and we have problem solving. With programming, you are mastering embedded system programming languages and using the right tools for efficient development, which is essential. While hardware design is also essential because designing circuits, selecting components, and understanding how hardware interact with software is also crucial. Now, you need to also have problem-solving skills. Troubleshooting issues, analyzing data, and finding innovative solutions is essential for success in embedded systems because you will see that you will face a lot of issues and you need problem-solving skills, which is something that every embedded system developer must gain. So, what are the common pitfalls in embedded systems? Many people focus solely on theoretical knowledge or only on one aspect of embedded systems, such as programming, neglecting other skills, other critical skills like hardware design and integration. Now, this will cause limited perspective. Focusing on just one area can lead to a limited understanding of how embedded systems work as a whole. There's also the incomplete solutions. Lacking a comprehensive skill set can result in solutions that fail to address all aspects of a problem. And there is also the difficulty in troubleshooting. When encountering complex issues, a narrow skill set makes it harder to point out and resolve problems effectively. So, now, why a balanced approach works? You need to find the balance while learning these skills. A balanced approach ensures that, let's say, a well rounded education embedded system enabling you to tackle real world challenges and with confidence. Now, this involves a combination of theoretical knowledge, practical experience, and hands on projects that cover all essential skills. Now, the comprehensive understanding, which means gaining a deep understanding of both hardware and software components, is crucial for creating robust and effective embedded system. There's also the improved problem solving, which a balanced skill set enables you to approach problems from different angles, leading to more effective solutions. We also have the increased adaptability. Being proficient in both hardware and software makes you more adaptable to current projects and industries and makes you a, an excellent embedded system developer that everyone wants to hire. Now, what are the benefits of a well rounded education? Our courses provide a balanced approach to embedded system education, ensuring you develop all the necessary skills to succeed in this existing field. There's also the theoretical foundation. You will gain a solid understanding of the fundamentals of embedded systems through comprehensive lectures and discussions. There is also the practical experience where you engage in hands-on projects that allow you to apply your theoretical knowledge and build real-time and real-world systems. And there is also the industry relevant skills, where you develop the skills that are highly sought after by employers in the embedded system industry. And this is the best approach to get started. Now, there is also real world proofs. Our graduates have successfully applied the skills they learned in our courses to various industries, from automotive to consumer electronics. They have secured high paying jobs and launched their own successful businesses, such as automotive by developing control systems for vehicles, consumer electronics by creating software for smart home devices, and medical devices by designing embedded systems for medical equipment. And these are only a small example of what our students were capable of after joining our academy. Now, there's also tips for success. Regular practice coding and hardware projects to hone your skills. You can use simulation tools and development kits to build and test your designs before implementing them in real world applications. Now, you need to code regularly. Practice coding regularly to improve your proficiency and build confidence. You also need to build hardware projects where you experiment with hardware projects to gain hands on experience and understanding. Plus, you can use simulation tools which utilize and help test and debug your designs before implementing them on physical hardware. In addition to that, you can simply explore development kits. Work with development kits to gain practical experience with different hardware platforms. These four methods can help you get started and succeed in the embedded system industry, even if you are starting on your own. Now, to build your first project, it might be challenging. So building your first project is a crucial step in your embedded system journey. It provides practical experience and help you apply your skills. First, you need to choose choose the right project that matches your skills. Then you need to gather resources, learn the programming language, learn more about the microcontroller, and learn about the project needs. After that, you need to design and implement. You will get started by planning your project design, write your code, and integrate the hardware and software components. After that, you will do some testing and refining, where you test your project thoroughly, identify your issues, and you will then refine your design for optimal performance. At the end, you will be able to document and showcase, which means documenting your project, process, and results. Consider creating a portfolio to showcase your work. Now, why projects are important? We talked a lot about projects in this webinar. Why do you think making projects is very important? Practical projects allow you to test your knowledge, understand the intricacies of embedded systems and build a portfolio that can impress potential employers or clients. There is practical application. Projects give you a real-world experience in applying your knowledge and solving practical problems. This is why all of our courses are project-based. There's also the portfolio building. The portfolio is basically a place where you showcase your projects or your old work as samples for employers or clients to wow them and to make them hire you in a blink of an eye. As much as you have projects and as complex as these projects are, your chances of getting hired will increase accordingly. Now, you need to avoid some of the common mistakes that a lot of engineers were, let's say, fall in. Most beginners either start with overly complex projects that are hard to complete or very simple ones that don't challenge their skills enough. So avoid overly complex projects. Don't get started with a complex project because you might not be able to finish it, and this will disappoint you. Don't choose projects that are too simple. Don't go for a very simple project that won't challenge your skills or won't cause you to learn things to apply that project. Always choose a project that is intermediate, that will challenge your skills and will help you grow, plus to be achievable. You can make it. Start with gradual complexity. Begin with, let's say, smaller, gradually complex or intermediate complexity projects that can help you learn while you apply and that are achievable, that you can do without any, let's say, disappointment at the end. Now, let's talk about project-based learning, which is a powerful approach for beginners. Project-based learning can be fun and effective way to learn new skills. Starting with the right project is key here to maximizing your learning experience. And let's discuss how to choose and complete successful projects. Why doesn't it work? Now, if you are choosing a project and you are working on it, but it's not working, then you either fall in one of these two things. It's an overly complex project. Starting with complex project, as you already mentioned, can be overwhelming and lead to frustration, or it's too simple. Overly simple projects don't provide enough learning opportunities. You may not gain the depth of understanding needed for more advanced projects. So if you keep doing overly simple projects, you will not grow your skills and you will not learn a lot along the way. So what should you do instead? As we already mentioned, you need challenging but manageable projects. You need to choose gradually complexity, which means that you will start with a simple, then a more complex, then a very complex project. As you finish each of these one, you will move up in the ranking of the complexity. And you also need guided learning. You will need to follow structured courses or tutorials that guide you on how to make these projects that are perfect for beginners. Then you can go from there to more complex projects. Now, and another proof that it works, there are home automation systems. Our students who followed a project-based learning approach have created impressive home automation system using Arduino boards, and we have a lot of courses on IoT or Internet of Things and home automation with practical project in a step-by-step manner. There's also robotics projects. They have built robots with various functionalities demonstrating their understanding of both electronics and programming. There is also job opportunities. These projects help students gain valuable skills and experience, leading to internship and job offers from different companies, and we have a lot of success stories. Now, a quick tip, just to break the ice. You need to document your project progress. Taking notes, photos, and videos help you keep track of your work and create the portfolio that we mentioned before to showcase your skills. Once you are done with a project, if you didn't find any picture for it, it would be really hard for you to document this in your portfolio to show this project that you have done to your potential client or to the companies that you are applying for a job in. They will ask for your projects because you are an embedded system developer, and your projects will showcase your skills. Now, a bonus tip: leverage online communities and forums. Engaging with other programmers provides valuable insights and help you troubleshoot issues quickly. So, if you are programming Arduino, go sign up in Arduino forums and start interacting with different programmers with like-minded people so that you can start communicating in a way that would help you improve your skills by looking at what are the issues that these people are facing, helping them fixing their issues, and maybe someday they will help you also fix your own issues. Now, there are common mistakes. Trying to learn everything on your own can lead to frustration and slow progress. Collaborative learning and seeking help is crucial. And this is also another thing that we provide in our academy, which is a Q&A. You can ask any question in our community, and we and everyone else would be more than happy to answer your question and guide you along the way. So let's see some personal story. When I started back in around 2007, when I was in the university, I struggled with the same issues. Joining online communities and collaboration with others significantly improved my projects because I kept looking for people online. I kept looking for their questions, what are the texts that they are using in the embedded system. And from their question, I could grasp what are the skills that I need to acquire to become a better embedded system developer. And that helped me reach this point in which I have an academy with than 200 courses and more than 500,000 students who are learning embedded system from me. Now, the turning point: actively participating in forums and asking for help at the beginning helped me accelerate my learning and allowed me to build valuable connections with a lot of people in the industry and a lot of companies that are now treat me as their consultant. They come here to me to turn their ideas into products in no time. And I take that idea, I and my team convert this idea into a device with a user manual. We reach a point where we help let's say, any company with a product idea to make that product, to make a user manual, and to make a website to showcase this product, which is basically an embedded system based product. Now, I was able to complete complex projects more efficiently and with greater success. I even started monitoring others, further reinforcing my knowledge, and I kept helping people until this day. Now, what resonated most? The importance of embedded systems. The wide range of applications and the impact of embedded systems on our daily lives resonated with many attendees. The essential skills. The discussion on key skills, such as programming languages, hardware understanding, and problem solving, was insightful for those seeking to enter the field. And these are the three main skills that you need to aim for. First, project guide. The step-by-step guidance on building a first embedded system project provided valuable practical experience and encouraged hands-on learning. Now, you need to embrace the future. Everyone will tell you this, and I'm telling you this also. Careers in embedded system. Embedded system professionals are in high demand across industries, offering exciting career opportunities. The future exploration. Many attendees expressed interest in more than one of our webinars and in most of our courses in gaining deeper knowledge. They kept asking us to make more advanced courses on a certain topics. And this is what caused us to have that many courses. We have courses in different categories in embedded system. Resources and guidance. There is a lot of people interested in learning more, and they requested detailed guidance and one-to-one, let's say, consultation, which we provide, live consultation, to help them after they take our courses to guide them what to do next. So unlocking your potential is maybe one course away. We provide comprehensive courses, more than 200 courses. We provide practical skill and knowledge, and we provide expert guidance along the way. We answer every question and we provide weekly sessions to help our students. Now, your learning journey would look something like this. You will start with video lessons from courses. Then you will go to apply the hands-on project, which we help you apply during the course. Then you join our live sessions to answer any of your questions that you might have. And you ask questions in our community. We have a vibrant community where you can ask a lot of questions. We have a community on YouTube, on Facebook, and on our academy. And we also provide 24/7 support. So if you face any coding issue, we are here to help you. Whenever you need a question, we are only one message away. Now, we also provide some exclusive perks. Now, the bonus material. And at the end of this webinar, I will also offer a bonus for our students who have joined this webinar. The bonus material, you can easily unlock exclusive access, downloadable worksheets, detailed guidance, and practical case studies and projects in our academy. We also provide scheduled events like weekly meetings and webinars, plus you can book a free call once you join the academy to discuss what you need to do next in your career. We also provide certificate of completion for every course. So imagine having 200 certificates in your resume in different categories of embedded system. Wouldn't that be amazing? Now, if you want, this is not something that we force you to do, and you would love to invest in your future, we have provided different plans as per our student demand. Now, we provided monthly, semi-annual, and lifetime access. And as you can see, the prices are to full access for the 200 courses. So you are paying a small fee and getting access to 200 courses, to practical material, to weekly sessions, to 24-hour 7, let's say 24/7 days support, and all of this at a very minimum price. So the monthly price would start with $9, the semi-annual price $49, and we have a lifetime which you will pay once and you don't have to pay again. It's a $499 price point. So these are the pricing for our academy with more than 200 courses and all the features that we mentioned. Now, if you enrolled now, you can send us a message and we can provide you with 50% discount for life. So if you are subscribing with a monthly plan, it will be for $499. If you are subscribing for the semi-annual plan, it will be for around $25. And if you are subscribing for the lifetime deal, it will be as easy as $255 or $250, sorry. And this will be for life. So you will get free bonuses, you will get project templates, you will get a 14 days money back guarantee if you didn't like the courses, and you can get started with your journey with us. Now, your questions matter. So again, we are here to answer any of your questions. You can directly email us at info@eduengineteam.com, which is the same domain as our website, eduengineteam.com, just add info at, or you can reach out to us through messaging on different platforms. And we also have a live chat on our website where you can ask any question. Thank you, and let's talk about the next steps. Thank you for joining us today. We are excited to help you embark on your embedded system journey. You can visit our website or contact us for more information. Again, everyone who joined the webinar is welcome to have 50% discount for life on our Academy subscription. Once you join, you will receive a cheat sheet let's say, in which you will have a step-by-step on how to become an embedded system developer using our courses. So we will tell you, like, watch this course first, then this course, then this, until you reach this course. And if you follow this blueprint or this plan, you will become an embedded system developer in less than 3 months. This is a promise. That's it. This was Ashraf Said Madhoun, the CEO of Educational Engineering Team. Thank you everyone who joined our session today and our webinar today. Hopefully we'll see you on another webinar. Thank you again and have a good day.